Professor Gaonkar.
I sent.
Yeah, no, that login was not working. Yeah, so now, yes. Now I can.
Yeah, Dr. Lalit Kumar, let us start.
Yeah, I am there. Hello, good afternoon.
Good afternoon, let us.
Good afternoon, sir.
Good afternoon, sir.
See, we are having little bit of.
Can you hear me, Lalit ji?
Yeah, we are able to hear you, sir.
Harish, you have to also allow us to share the presentation.
Yes,
Your
sir.
rights you have to give.
So, good afternoon. Can you hear? Surendra
Yes,
Pal, you are
Dr.
muted. Professor Shivgaonkar, good afternoon.
No, I'm not muted. You have to start now.
I think some of you are muted.
The recording would start late, sir.
Rishi, I think Professor Paul seems to be muted.
No.
I think there is some audio issue there. We are all speaking.
I can't hear Professor Surendra. You are speaking something, but I can't hear.
Sir, there is audio issue, I think, on your side, sir.
Is it?
Yeah.
Okay. Okay, let's see. Hello, Dr. KP. Yes, I can hear you. Raj Singh ji,
Yes, sir.
can you hear us? You can hear us. Okay. Dr. KP Ray,
Yes, sir, I am able to hear.
you can hear us. How about you, Dr.
Raj Singh ji, am I audible now?
You are audible.
Hello.
Yes,
Yes.
you are
Yeah.
able.
Raj Singh ji, am I audible now?
आप कौन बोले सर?
Being from space, I am keeping a redundancy of laptop and three headphones.
I can see that now.
So you have gone to 2x3 redundancy.
Yeah.
Not see in Inmarsat when we had this thing for Insat 2E, they wanted 3 receivers instead of 2. Normally we go for 2, 1:1 redundancy, but they wanted 3 receivers for TTC for purpose to have a higher redundancy.
So at least I'm having a redundancy, not triple redundancy. So let us start.
Yes, sir.
I see Dr. Chandrasekhar, namaskar.
Namaskar. I hope you can hear me.
Yes, correct.
Great.
Yes, sir, good afternoon.
Good afternoon. Good afternoon, everybody.
Good afternoon.
So should we start,
Lalit
sir?
Kumar ji, let us start. Yes, please start.
So, dear all, am I audible, sir?
Yes.
Yes.
Dear all, welcome you all to this webinar on RF microwave to terahertz education for the next generation. We welcome our speakers, Professor Gaonkar, Professor Subramanian, Professor Subal Kar, Professor Sivan Kaul. We are thankful also to our distinguished speakers for accepting our invitation. It is our privilege to welcome Dr. Chandrasekhar to this webinar, and we are thankful to him for taking the time out of his busy schedule. We welcome to Dr. Pancharya and thanks to him for joining this webinar. We also welcome to our panelists, Professor B.N. Basu, Professor K.P. Ray, and other members of the panel, and wish we will be able to discuss the matter of the webinar to a fruitful conclusion. We also welcome Professor Mahadevan. I welcome all dignitaries, the faculties and all the students to this webinar, and hope you all will join, you all will enjoy and contribute. I also welcome our INA webinar team. Now I invite Dr. Lalit Kumar for his opening remarks. Lalit Kumar, sir.
Not audible, please.
You are muted.
Sir, you have to unmute.
Not audible.
Lalit Kumar ji, you are muted.
No. Still muted.
Sir, you have to unmute. We are not able to hear you, sir. You have to unmute.
Yeah, no, I'm done here.
Yeah.
So am I audible now?
Yes.
Yes.
Raj Singh ji, am I audible now?
Yes, sir, you're audible.
Great. So I'm glad to say that the chemical engineering group on this microwave to terahertz technology and applications has taken the lead to organize this conference under the chairmanship of Dr. Surendra Pal, who is heading our academic wing of this group. And the purpose of the group is to develop a position paper on the entire microwave millimeter wave prosperity growth is like so if the 19th 20th century were driven by electricity, the 21st centuries and beyond will be driven by communications, and particularly the high frequency RF, microwave, millimeter wave, and lasers. So we have a good task cut out for us. And the idea is basically for this webinar to develop some kind of a scheme for the microwave terahertz education, which is dreaded by most engineering students because of a lot of mathematics, to develop this education for the new millennium and the new people, the generation. And there, all kind of modern teaching technique, the virtual laboratories, the computer simulation based concepts, and design and artificial intelligence and metaverse and all those such things, concepts, we have to try to incorporate there. And I would go to the extent that even at the lower level of the class 12, 10, 11, and 12, we should integrate optics and electromagnetics as a single subject and try to introduce the topic of this technology at even that level. So this is for the task for the academicians who are going to present, distinguished people who are going to talk today, and the panelists who are going to discuss this matter. We would together try to evolve some kind of a strategy for developing a curriculum or developing a strategy for microwave millimeter terahertz education for the next year. So that's the objective. So I request that all of you will be able to put forward your best ideas, and this discussion would give us some very good starting points to be included in the position paper, which will act as a reference for the policymakers and planners in future. So thank you very much. And I must thank all the panelists for agreeing to be part of this event. Thank you very much. So over to Harish. Or Raj Singh.
Thank you, sir. I would now invite Professor Pal to please say a few words and share with the audience.
Good afternoon to all the academicians and researchers in the field of RF and microwave. I'm happy to see some of my colleagues also, including Professor Mahadevan. In a long association with RF, and when we started RF, we had to force the engineers to work in the field. Nobody was interested in working it, and they were not trained also, let alone they were trained on the job. So Dr. Lalit Kumar put up a proposal to INA that we can have a one group to look into all the aspects of RF that starts from microwaves, millimeter waves, and terahertz. And so I feel that we should devise a curriculum. I don't think it's from my side.
I think others can mute, who are not talking.
So we should devise a curriculum which should be at least of 8 credits, spreading on 2 semesters, where the knowledge of we should introduce mathematics, calculus, matrices, etc. We should introduce the fundamentals of electromagnetic waves, equations, not detailed derivations. I had a detailed discussions on this issue with late Professor Tapan Sarkar, who was a good friend of mine. Both of us argued on this, and I said, I never used the Maxwell's equation derivation in my long career. Similarly, about electromagnetic noise, polarization, EMC, AMI, then, now when we come to 6G, 5G, 6G, etc., and beyond, the millimeter waves, terahertz, and microwave photonics becomes very important. All these things are not taught. They are mostly taught here and there, but not as a part of the curriculum. Now, since we have got under NEP 2020, in that one, we have got autonomy, autonomous colleges, universities, deemed universities, etc. They can formulate their own courses, and the laboratories and industry can help them. So we should devise a course where we introduce to a subject, but we go into the details of the physics of the subject, starting from low frequency to microwaves to millimeter waves and terahertz, and go for quite a bit of details about how to communicate. Communication becomes very important. So the fundamentals of microwaves, terahertz, imaging, etc., also becomes important. And then when it's coming to 6G and 5G, then MIMO becomes important. Then radars becomes more important in the present era. And miniaturization becomes a part and parcel of it when devices comes into picture. So the physics becomes a figure. So it becomes a very complex thing. After Dr. Lalit Kumar requested me to look into it and prepare a small paper, I did send to Dr. Sharma. This can be circulated. When I went through all the things, I found that it's not one course. Actually, it should be at least minimum 8 to 12 credit courses, or maybe some of the things should be taught in the undergraduate level, and then postgraduate level, it should be 2 credit, 2 semester course, 8 credit course. Then only we can cover it. And it becomes important today. It's not only the RF, because now, machine learning, artificial intelligence, all those things are also becoming part and parcel of microwave. And when the 6G is knocking at the doors, we have to import everything for 6G. And that should not happen when we want to do for Atmanirbhar. At least some sort of effort should be put in this direction. And I'm quite pleased to see that Professor Subramaniam, Professor Shevgaonkar, Professor K.P. Ray, Professor Carr, and Professor Mahajan. Of course, Mahajan and myself, we are all retired persons, but still we can contribute in our own way. So I request and expect that 2 distinguished speakers who are going to speak, great academicians, both of them are known, very well known, to look into all these aspects and give them. Finally, we'll prepare a paper and submit to INE, which will request the INE through Dr. Lalit Kumar that it should be widely circulated to all the autonomous colleges, institutions, and deemed universities. Of course, IITs and NIITs are included. Thank you very much.
Thank you for the kind words. I would request you to please also chair the following sessions, which would now take place with the help of the expert speakers. So I would now like to request Professor K.P. Ray to please take over and please introduce Professor Shevgaonkar, who would start with the first sessions. Professor Ray.
Yeah. Thank you, Harish. So before the lecture, I'll be very brief in introducing Professor Shevgaonkar. For me, it's a proud moment for a student to introduce his teacher and mentor. In fact, Professor R.K. Shogawkar does not require any introduction. He studied and learned everything in India and taught electromagnetics to the whole world. Besides being an accomplished academician, he is an able academic administrator as well. He was Deputy Director of IIT Bombay, Director of IIT Delhi, Vice Chancellor of University of Pune and Benetton University. He is IEEE Fellow and Fellow of almost all the Indian academies. Very few people know that besides being an authority in academic field, he also holds a degree in fine arts. With this very, very brief introduction, I hand over the floor to him for the lecture. Sir, please.
Thank you, KP. Can I get the sharing rights? Okay, I can screen.
Sir, it is done.
Yeah. Just 1 minute. Can you see the screen?
Yes, sir.
Can you see the screen?
Yeah. Yes, sir.
Now?
Yes, yes.
I will make it full screen and then we'll just start. Is that okay? Everybody can see the screen?
Yes, from my side.
Yes, sir, we are able to see.
Excellent. Very good. So thank you, KP, for nice introduction. And I really cherish our association, which has been there for very long. So the Honorable Chairman of the group, Dr. Pal, Dr. Lalit Kumar, all distinguished colleagues from different IITs and different institutions, and the participants, which are quite large in number for this seminar. I'm really delighted and privileged to be the opening batsman for this particular webinar, which is on RF and microwaves. I'm still not sure to whom this webinar is targeted to, but I assume that there are lots of PhD students who are there, and they would like to know the opportunities which are there in the field of RF and microwaves in the country. So let me admit that this is not the talk which is prepared only for this webinar, because the time was actually too short. So I had prepared this webinar some time back for IMARC to take account of what is the research going in our country. And that's what I have updated a little bit to really suit today's requirement. So just look at the electromagnetic spectrum. We all know that when we look at the electromagnetic spectrum, it is very wide. It starts from almost 10 meters wavelength, which is about 30 megahertz, and goes up to all the way up to 3000 terahertz, which could be even beyond optical range and so on and so on. However, today, when we are talking about the RF and microwaves, we are going to restrict ourselves maybe up to the millimeter wave, which could be about few hundred gigahertz or something like that. And that's where we are going to focus on. So what I'm going to do is, first I'm just going to give the activities which are there in the microwave field in the different areas, so people get a good understanding of what are the different possibilities where the microwave and millimeter wave and terahertz technology can be applicable. And then I will just come very quickly to which are the institutions in our country who are involved in this kind of research. And finally, I'll make some comments about the educational scenario as far as this RF and microwave is concerned. So when we talk to laymen and the microwave word is uttered, I think commonly people just understand microwave means only two things. One is the microwave towers, and because they are now practically mounted on each and every building which you see, tall building in the city. And also some people think that the signals can be received through the satellite. There are some earth stations, which are there, which can receive signals which are coming from the satellites. Another thing where people know about microwave is the microwave oven, that it is a household in practically every house nowadays, and where the microwaves are used for heating, the cooking food and so on. So these are the two things which commonly people know where the microwaves are employed. Whereas when we go for the research, there is a very wide canvas of the research activities in RF and microwaves, because the spectrum is extremely wide, which goes from some tens of megahertz to almost like tens of gigahertz, something like that. So let me first take the biggest environment or biggest field, where the microwave and RF is employed, and that is the cellular communication. I mean, cellular communication, which is now so pervasive, I think practically everybody has a phone in their hand, the mobile towers which are there. The challenges which people have to face are essentially the interferences which are going to be created by the different frequencies and within the different cells. Also, people have to worry about what is called the electromagnetic environment, because when the electromagnetic radiation goes, the bodies which you see around, most of the bodies which are there, which are RCC nature, which are almost like steel bodies, and the radiation which goes and gets scattered or reflected from these bodies, they create the dark and bright spots in the vicinity, and because of that, the signal keeps fading. And this is one of the challenging problems which one has to worry about when we talk about the cellular communication. Also, the cellular communication requires the systems like the antennas, which are the adaptive antennas now. And concept of the antennas in this, like you have to control the radiation pattern by shaping the antennas, and all that thing is modified. Essentially, what you do is you now do more adaptive signal processing and to create a synthesized beam, which essentially maximizes the signal to noise ratio. So MIMO is one of the challenging aspects of electromagnetics also, because the whole MIMO works on the principle that from the different antennas which are there in a system, the signal, decorrelated signal, can really propagate through the channels, and therefore you essentially can enhance the channel capacity. Whereas when I come to now the communication side, essentially now we are migrating from the 4G to 5G. And that is something which is really taking the system people to really deep into the microwave domain. So if I look at what was there in the 4G, the data traffic was about 7.2 exabytes per month. That's what transmitted. The data rates were about 1 Gbps per second. The bandwidth spectrum was about 3 gigahertz. And there are density of the people of about 1,000 connections per square kilometer. Whereas when we migrate now into 5G, which is now going to be very, very soon, we require the latency of this whole network has to be less than 1 millisecond. The data traffics are going to be 50 exabytes per month, and that is the prediction which was there in 2021. The peak data rates are now going to touch about 20 Gbps. The available spectrum is going to be about 30 gigahertz, and the density of the users is going to be 1 million connections per square kilometer. So one can see now what a dense environment which will be created over a wide electromagnetic spectrum if you have to really cater to the services of the 5G, and which will again take it further into the 6G domain, which will make the requirements still further stringent and broad. Then comes to the domain where the electromagnetics and RF is applicable is the fiber optic communication. And normally people think that when we talk about optical communication, it is the optics which is more important. However, the optics is only a very small part of the optical communication. When the light goes inside the guided devices like optical fibers or the integrated optical devices, that's where the light is going to play a role. However, the whole system or the data rates which are going to go on the optical communication are practically limited by the RF circuitry or the microwave circuitry. Because what we require the high-speed modulators, we require very high-speed detectors, we require switches. And all this network which you are talking today in optical communication, they are now in the range of about 10 gigahertz or 10 Gbps and even beyond that. And then we are talking about the modulation schemes which are not even binary. We are talking about the more complex modulation scheme like QPSK and so on and so on. And this thing has to be done all at the microwave frequencies. So earlier when people used to think about microwave, it was just like simple point-to-point communication, maybe a few gigahertz bits kind of transmission. When we go into the optical communication domain, we have to work with the microwaves which are in the range of about tens of gigahertz. And that's where this subject is going to be important. Of course, the next application of microwave is radars and remote sensing. And this is very widely, the defense applications are very wide. We are having many laboratories which work actually in this area. And also this principle is also used for remote sensing. So here we require the modeling of the terrains electromagnetically. We also require the modeling of the atmosphere where the signals are going to propagate. And then from there, we have to reconstruct the good quality images of the terrains. And that is one of the applications where we will see the microwaves. Then the application which is not much known to people who are not in this field is radio astronomy. And radio astronomy essentially is the studying the universe at multiple frequencies. And these frequencies can range essentially from the lowest frequency which the ionosphere can handle to the highest possible frequency which probably you can really have an instrumentation of. So radio astronomy actually ranges from 30 megahertz to almost 100 gigahertz, right, which goes into the millimeter wave range. And variety of telescopes and systems have been created, right, in this wide range of frequencies. So although the radio astronomy, the science which we want to do with this is basically the pure science, but the instrumentation which is required is really the state-of-art microwave and RF technology, right? And what is the radio telescope then? It is nothing but an antenna. It requires a frequency selector, it has a detector, and it has a data recorder. So most of the effort in designing the radio telescope actually goes into designing the antenna. And the technique which is very common in the radio frequency domain, the aperture synthesis technique, it has become really the core to the radio astronomy. So by essentially creating apertures, synthesized apertures, people have created the apertures of the size of about tens of kilometers, sometimes even transcontinental kind of distances, and they could really see the universal object with very, very high precision and with great sensitivity. In India, we are having one of the most first telescope which was created, which was in Ooty, which was by TIFR, right, which used to work at 300 megahertz. Later on, Professor Govind Swarup created another big telescope, which is one of the largest telescope in the world, right, which works at a very wide range of frequencies from 75 megahertz to up to few gigahertz. And this is one of the marvels of the radio frequency technology, because they have created the dishes which are 45 meters diameter dishes, 30 in number, and they are spread over a distance of about 20-30 kilometers. So basically, the receiving the signals over this wide range of frequencies with proper polarization, with proper sensitivity, with good signal to noise ratio, carrying the signal back to the base station, performing the correlation at microwave frequencies. These are some of the challenges which the radio astronomers have to face when we go to the radio astronomy kind of field. Then we are having the area where now the RF and microwave is finding a great application are the metamaterials. Now under metamaterials, you are having various things. So you have photonic crystals, you have frequency selective surfaces, you have negative index materials, you have anisotropic material, you have tunable materials, and so on and so on. So when we come to photonic crystals, though the name photonic suggests that probably these are the structure which work like optical frequencies, but incidentally, this phenomena of the photonic band gap was first observed in radio frequencies. And people knew that you could create this kind of the band selected structure by using the periodic structure at microwave frequencies. So a photonic crystal essentially is the periodic structure where the periodicity is of the order of wavelength, and at microwave frequencies, you can really create this kind of periodicity by using today's technology. So simply said, if you consider a layer by layer a periodic structure with two different dielectric constants, then essentially you create a material with certain band gap, and the band gap can be manipulated by the difference in the dielectric constants of the two material and also the periodicity of this the material. So by manipulating these two parameters, essentially the band gap of the material can be manipulated. And this is something great, because by doing this, then one can create the frequency selective objects, which is one of the requirement of any communication or any microwave system. When we come to metamaterial antennas, the same periodic structure can essentially be used by suppressing the higher order modes in the substrate. So normally, if you consider a microstrip antenna on a substrate, then there are lot of energy goes into the surface modes. And this energy is a leakage or is a less, it reduces the gain of your antenna. And also it sort of increases the side lobe level of your antenna's radiation pattern. So to avoid that, one can create some kind of a periodic structure in the substrate, right? And by doing that, essentially you create a photonic band gap, right, towards in the planar direction. And because of that, the energy which otherwise would have leaked in the substrate now is prohibited because of the band gap phenomenon. And now the energy which is now not leaking in the substrate can now be guided toward radiation, and then you can suppress the surface modes and the efficiency of the antenna can be enhanced. So this is one of the areas where current lot of research is going on. You can also apply the same principle by creating one-dimensional photonic crystal by creating a layered dielectric constant, and you can have a printed circuit antenna, and you can have the multiple layers deposited on that, and this again can help in stopping the energy going in other direction, so that because of the band gap phenomena, and the energy can be radiated essentially perpendicular to the patch, and the efficiency can be increased. So this phenomena can be thought of as a Bragg reflector, and by doing this, the efficiency or the directivity of the antenna can be increased by many fold. So this is one of the ways, these principles of the Bragg reflection can be applied to the antenna technology. Then the application comes to negative index materials, and if you identify the materials which are having the negative permittivity and negative permeability, then the combination of two can give you the refractive index which is negative, right? And it has been shown that if you take this kind of material, then this kind of material can be used essentially for focusing the energy by using the planar lenses. So as is shown on the left side, if you consider a point source, because of the negative index, now the rays which are going in the material, now they get deflected in the opposite direction, and they again focus back inside the material. So this phenomena essentially can be used for focusing the optical energy or electromagnetic energy, right, even by using the flat lenses. The phenomena can be realized at low frequency, at RF and microwave frequency, by using a combination of what is called the split ring resonators, and by using the straight wires. So it has been shown that if you consider the collection of wires, then the permittivity of this over certain frequency ranges becomes negative. Similarly, if I use the split ring resonators of appropriate sizes, then we can again create the negative permeability over certain range of frequency. So if you create the combination of these two, then for which the permittivity is negative, the permeability is negative, and this combination can be considered as a negative index material. So this at microwave frequency, it is a lot more easy to realize, because you can create the split ring resonators, at microwave frequency very easily. You can also print this straight wires, on the substrates, and the combination can be demonstrated to give you the negative index material. There are many people who have research on that, and this negative index materials have been realized in practice. Then there is a tremendous amount of interest in the anisotropic material for cloaking, essentially to consider a system where the electromagnetic energy will be guided around it, and without creating any shadow, essentially you can create the transparent bodies, and this is one of the interests even from the defense applications and so on and so on. So these are some of the applications. So just to summarize that what kind of applications which we have, right from the broadcasting to microwave links to 5G, satellite communication, radars, remote sensing, optical fibers, lasers, microwave photonics, radio astronomy. These are applications, and also we have applications in the medical application. So we also have now the NMR kind of applications. We also have many the effect of the microwaves on biological species. So you see application there. There is the IR vision, the terahertz technology, metamaterials, invisible cloak, and so on and so on. So there is a huge amount of scope for research in the microwave and the RF and the terahertz area. And these are some of the areas where research is going on very, very broadly. So wideband antennas and arrays, this is one of the areas in which people are interested. The antennas for wearable electronics is something which is of interest. The EM scattering model for different electromagnetic environment, that is something where people are working very actively. Microwave photonics, as I mentioned, in optical communication, the optical fiber is only one small part of it. But what we require are the printed circuit devices where the interaction of microwave and light takes place. And that's where a lot of the technology development and the research is going on. Terahertz technology, of course, I'm not expert in that, right? But that is the area in which you see spectroscopy applications will be there in terahertz. Biological effects of microwave radiation, people have been working for many decades to really improve the yield of the agricultural products, also sort of creating microwave dryers, and so on, right? So that we find an application. The RF power harvesting is something which is of interest to people. And when the 5G and 6G will be deployed, you will see that now the millimeter wave technology will be every corner of your room, every corner of your house. Because the data which is going to coming, which is wideband data, that data to take it from your devices to the optical fiber, which will be a very broadband pipe, you will require a very large bandwidth kind of RF pipes. And they will be in the form of microwave pipes or the millimeter wave pipes. So these are the areas in which are going on. Now coming to the national scenario, so that means we are having a great motivation, and also we have a demand, for the RF and microwaves right in the country. And it is not that the India we are talking about microwave first time. Actually, India has been the pioneer in the microwave technology. In fact, the credit to the millimeter wave technology goes to Sir Jagdish Chandra Bose. He first in 1897 demonstrated the 60 gigahertz the transmission, right? And he could really demonstrate that the signal can go right in the form of microwaves and millimeter waves, right? And he could really explode something by using a remote switch by using the millimeter wave signal. So he was pioneer in microwave research. In fact, his detector was used by Marconi in his first ever experiment of microwave transmission across the Atlantic Ocean. He generated 60 Hz signal and detected through Galena detector, the first semiconductor detector one can think of. He also demonstrated point contact detectors, which were the precursor for the diode detectors, which you see very commonly used now. He demonstrated the guiding and reflection of microwaves through lenses and prisms, and studied effect of microwaves on biological species. So you see that the activity in the microwave is as old, is about 150 years, right, in India. However, when I look at the research today in our country, right, which we can say which is post-colonial essentially, so after 1947, one can divide our research into different categories. One, we can say our research is mission-oriented research. It could be application-oriented research. It is fundamental research. It is microwave research in allied fields, or it could be consumer and commercial application-oriented research. So when I come to mission-oriented research, the ISRO, the Department of Atomic Energy, the Indian Research DRDO laboratories, and scientific CSIR laboratories, these are the institutions where there is a mission-oriented research in microwave goes on. Then you are having application-oriented research, which is satellite system, radars, where there are even public sector like Bell is very active, the remote sensing agencies, the microwave links, civil aviation, RFID, EMI, EMC, the structural defect monitoring by civil structures, non-destructive testing, again used by the material scientists and by the civil engineers. These are some of the application-oriented research which you see taking place in the country. Then you are having fundamental research, as I mentioned, like radio astronomy, designing metamaterials for various applications, the ionospheric research, which is done at NPL, the tropospheric research, which I remember long time back, IIT Kanpur used to do that on tropospheric link, modeling of electromagnetic environments, Samir is one of the institutions, biological effects and the enhancement of the agricultural yield. The BRC was one of the institutions where the active research was going on. And then we have microwave research going on in the allied areas, like laser sciences, where DAE and DRDO are very active. Optical communication, there are some private companies also which are now working at the data rate, which are in the 10 gigahertz range for the transmitter and receiver. The high-speed optical receivers, that is where the more fabrication kind of work which is going on. Microwave photonics, where generation of the microwave signal by using photonic techniques, or by controlling the light by using microwave signals. Both ways, actually, you see a great research which is going on. Generation of microwave and millimeter wave signal in optical means, that is again by using parametric kind of generation, we can have research, which is in this area. Now, consumer electronics, of course, microwave ovens are very well known. Cellular communication is getting now more and more, as we saw, 5G, 6G. Wi-Fi links are going to be now working almost in gigahertz kind of range. and remote control electronics, which is now again becoming very, very common, and biomedical instrumentation, which is again going to be heavily dominated by the RF and the microwave frequencies. So just to sort of quickly say which are the institutions where the research goes on. So Siri Pilani is one of the institutions where there was a high frequency work which went on the TWTs and the KU band, KA band, 42 gigahertz, 110 gigahertz, right, and variety of activities which you see in Siri. You are having MTRTC Hyderabad, which is the laboratory of DRDO, which is involved in development of advanced types of microwave tubes, right, and main area of research are computer design, simulation, development of microwave tubes, microwave power modules, microwave generations, and major developments was essentially in the pulse KU band kind of airborne systems, for radars and so on. Then you are having DRDL, DLRL, Hyderabad, LRD, Bangalore, and BEL. They are involved into the radar systems, and we are now really having a state-of-art radars, which are developed by these organizations and the companies like BEL. Society of Applied Microwave Electronics Engineering and Research, SAMIR, right, where I've been interacting for many, many years. They are having wide range of activities in the antennas, microwave photonics, the ionosound, which is probably one of the things which they are really expert in, the LENAC tubes, which they develop and they commercialize, the EMI, EMC, the energy efficient RF dryers, which have been commercialized, the microwave oven, industrial heating, right, and so on. So this is an organization where most of the institutions actually is involved in the research which is related to the microwave. TIFR, we already mentioned, this is a radio telescope, the photo of one of the antennas which is used in GMRT, and they use really state-of-art electronics, which is working at gigahertz or gigabits per second kind of data rates. Then you are having IPR, Gandhinagar, where you have application of high-power microwaves for generation of plasma. And for this purpose, 28 gigahertz, 200 kilowatt gyrotron-based electron cyclotron resonance heating system has been successfully commissioned by Aditya Tokamak. And there may be more research also which is there, because the slides are not really up to date. So there is much more research which has come, from the IPR Gandhinagar. IIT Delhi has one of the, the state-of-art center in millimeter wave technology. And I think we are going to have Dr. Kaul, who will be talking about the activities right into that. So there the research was essentially creating microwave and millimeter wave devices, the electromagnetic band gap structures, right, and variety of antennas and the devices which are used. IIT Bombay was also involved in microwave phase shifter designs, ferrites, optically controlled microwave devices, microwave photonics, multi-band antennas, high-speed optical receivers, and so on and so on. IIT Kanpur, I remember when I was a student in IIT Kanpur, they used to have a specialization in electromagnetics, and which was probably considered to be one of the first preferred specialization who came there for doing MTech and PhD. I don't know what is the status today, but that was one of the institution where the microwave was considered to be really a very high level of academic level, from the post-graduation studies. IIT Kharagpur also used to have similar kind of activities, and they also have very strong programs in the RF and the microwave region. Then we are having IIT Kharagpur, as I mentioned, they also have very, very active group, and they used to work on antennas, the MIMOs, the radar system, microwave circuits, then mathematical techniques, and so on and so on. Then you are having an Institute of Radio Physics, Electronics, University of Calcutta. They also have a very wide range of activities in the field of microwave and RF communication. We also have University, Behrampur University, Odisha. They also work on the metamaterials and the antennas, and they work on the fractal antennas and electromagnetic metamaterials, and so on and so on. We also have University of Rajasthan, where there was activity on the silicon substrate-based devices, and also the component which are required for the microwave communication. Delhi University South Campus also had activities in microwave devices and waveguide components, and also optically controlled the passive microwave devices. Then you are having NIT Tiruchirappalli, where also have the activities of metamaterials, RF MEMS, right, and various other activities. So this is some of the, just a summary, just to give a flavor for the students who are going to work in these areas, that these are some of the places where you will see the activities and great research which is going in the area of microwave and millimeter waves and so on. So they can decide and choose the institutions of their choice for doing research in these areas. So with this kind of background, that so many institutions are really working in this area, which is a very wide range from RF to the microwave to millimeter wave to terahertz. Question one is asking is, how the education in this particular field is going on? And in fact, all these institutions which I mentioned, the research, this is the research part which is going on. You take it CSR laboratories, or you take DRDO, or you take even IITs. The postgraduate programs and the research activities are the ones which are very, very strong. Question at the moment is, where do we get this trained manpower which is going to support the research which is going to take place in this institution? And the students come from the engineering institution, from undergraduate programs, and maybe for the MTech program. So earlier, when we looked at the curriculum of electrical engineering or even electronics engineering, there used to be 2-3 compulsory courses on electromagnetics. There used to be one course on electromagnetics, which was a static field. There was one on time varying field. There used to be one course on antenna. There used to be one course on microwave techniques. So there were many courses which were more or less compulsory kind of courses which were there in the undergraduate program. So microwave theory technique, microwave devices, antennas, wave propagation, all these courses students really got prepared with when they went either for a job after their post-graduation or even after graduation into the industry or in the R&D laboratories. They had a good background of the microwave and RF frequency. However, what has happened over the years, because of this IT domination into the fields, and there is a job market which is now getting completely skewed because of the applications which are the IT-oriented application, the electromagnetics component of the curriculum reduced significantly. Now, most of the curricula, if you see in the undergraduates, barely one compulsory course on electromagnetics actually is offered right into the program. And under that, starting from your static field up to the antennas, covering becomes practically impossible. Second thing, what is the problem is that with new generation, the mathematical background of the engineers is reducing with time. So I remember if you today ask an electronic engineer, does he know the conformal mapping? And I'm sure 99% students will look at you as if they are hearing this word first time. That's what is going to happen. And that's what the solid mathematical background which is required for the subject like the EM, I think that somewhere is missing into the curriculum. So the microwave related courses are now becoming just an elective, and very few students actually take for these kind of courses. And some interest has been developed in the field like computational electromagnetics, because they think there is a computer involved in this and maybe the computational techniques are there. But for even doing computation, one really requires a solid understanding of the electromagnetic phenomena. And that requires a good understanding of mathematics and physics. So one of the priorities of this group probably would be to really create the curriculum where people who are very strong in mathematics and the physics, they can be brought together, they can be mentored right from the beginning so that they can really develop interest in these areas. And once that happens, maybe naturally they will make a transition to these areas and so on and so on. So these are some of the challenges when I look at which we have in front of the microwave community today. First of all, the manpower availability for the cutting edge research, that is one of the biggest challenge which we face. Low priority of the RF subjects in engineering curriculum, that is another challenge which we face. Subject is difficult, and there are many softer options available to the students now, which make them much more employable, where salaries are much higher, right? And with a softer option, they can really go to those subjects rather than coming to difficult subjects like microwave. Low involvement of industry in RF development. There are very few industries which actually work in RF areas, and jobs are mostly in the government sector. And today, when there are so many opportunities available in the private sector, that generally students have a tendency to go for private, which are much more lucrative jobs. And unless this private sector start playing a major role in the area of microwave and millimeter wave, right, this problem is going to continue. So in spite of all these challenges, I think India is doing very great as far as this area is concerned. It has been doing great. It did well in the past. and I'm sure in the years to come also we will keep doing well. So thank you very much for this opportunity, and if any questions we can really discuss. Thank you so much.
Yeah, thank you, sir. You touched upon all the aspects of the topic, and we can have quick one question.
Hello, am I audible?
At least Mahadevan here. At
Yes.
least one course on electromagnetics anyway is made compulsory in most of the institutions.
Correct.
That takes away one full semester.
Yes.
So then, when, as you said, when you offer microwave or antennas as electives, nobody takes.
Yeah.
And they also forget complete electromagnetics by the time they come to 4th and 5th semesters,
Absolutely.
6th semesters. So there should be a continuation. So they should be grouped as communication group, and then say that these are the courses you need to take, with electromagnetics being compulsory for everybody, so that at least you can have a group of people who will have electromagnetics, microwaves, antennas, and propagation, and then followed by computational electromagnetics as their project when they can do that. That's what I thought I would just say.
I fully agree with you. So as we create now the verticals like artificial intelligence and so on, maybe we should also create a vertical for the microwave, millimeter wave, and terahertz technology. So the sequence can be created, where people can keep taking courses one followed by other. So I fully agree with you. Yeah, you have to create a scheme.
I would like to make a comment. Professor Shivgaonkar has covered very widely the opportunities in India and also given very good ideas. And I think the purpose is to generate, more ideas which we would like to collect and then put together to make a proposal of what should be done about the microwave terahertz education in India. So I welcome all such comments. So time may not permit, so you can definitely post these comments in the chat box or later also. Thank you.
Okay, thank you, sir. Now the next session will start.
Raj Singh ji.
Thank you, sir. Thank you very much for your address, and thank you, Professor Ray, for helping us here. I would now like to invite Professor Chandrasekhar to please address the gathering. Chandrasekhar sir is there. Professor Chandrasekhar?
It's on mute.
Yeah.
You're not audible, you have to unmute.
Yeah, I guess I'm audible now.
Yes.
Yes, sir.
Okay. So, good afternoon, everybody, and it's wonderful to be part of this discussion. My own background being a little broader, I would try to, view the issue from a slightly broader perspective and a comparative perspective with other sub-areas of electronics and applied physics. So, Professor Shivgaonkar's presentation has made my job easy. I would therefore say that if you look at it, if I look at the typical curriculum, you find today a course on electromagnetic theory that's part of every undergraduate engineering program. However, this becomes kind of a standalone course. You don't see children really requiring that background being exploited further in subsequent courses. So it somehow looks like a course that dangles by itself, which is a foundational course, all right. But I have checked with students. Students generally say, sir, we can't see where and how we really are then going to apply this. This partly because they don't have other course offerings subsequently which are linked up. So that's one issue. But then if you really look at it, I would say that Professor Shivgaonkar mentioned about creating a vertical. I was thinking in terms of having a postgraduate program, but then the structure of the postgraduate program the kinds we have seen in the country, it's either more device oriented, and that again is insufficient because you don't know where the device goes, what do you do with the device, and rest of the things that go around. So I thought a comprehensive kind of thing would be where you really begin from the application end and you look at, let's say beginning with the application scenario. So in the application scenario, you have an n number of applications. Maybe one can initially have a orientation course that tells the student where are all the different applications in this. And I think that should begin obviously with the communication, all the different Gs, G2, G3, G4. So all different 6G, 5G, 4G, 3G, 2G, all different varieties of Gs. Then the cellular communication, then the broadband mobile communication, which is satellite based. So all the communication oriented things. So there should be initially a orientation course which introduces you to what are these technologies, in the sense not getting into the depth of technology, but trying to say that what are the basic kind of scientific principles and engineering design issues that are powering these kind of technologies. So I think that would be a stimulant for students to understand that electromagnetic theory lies at the heart of all of it, and that needs to be mastered rigorously, and that they would require computational electromagnetics whenever they try to work with these kind of systems. So then there should be, after such a initiating kind of course, there could be a course which basically deals with signals and their generation. Now these are signals for communication, so which include all kind of modulations and then amplification of power. So I'll just call it signal generation for communication applications. So signal generation for communication applications, signal propagation, signal reception, particularly signal reception in hostile environment, which is really the radio frequency environment where everybody has access to free space as much as anyone else has. And so how do you pick out an extremely weak signal from a very hostile environment where there are other signals with a lot of strength? So all that part of, reception of signal and its amplification and its possibly pre-filtering and then channel level filtering. And of course, it includes demodulation and frequency translation aspects, all of that. So all that, after the introductory course, the getting into the system implementation side of it sensitizes the students to, what kind of, let's say, call it methods or techniques are being used in actually utilizing microwaves for being able to achieve communication, large bandwidth communication, mobile communication, within, of course, wires and wireless kind of communication with very high bandwidths. So that signal generation part, signal transmission, signal reception, and signal detection, to me, 2 courses can be structured to really cover it in a decent kind of detail. That will tell all the different techniques that go in there, so that the student understands the principles at least very, very well. Associated with this, I know it is difficult, but there should be laboratory component for measurements in particular. That's a weak part, very, very generally. That's one thing other that students generally complain, they say that we are taught a lot of mathematics, but there is nothing we can, play around with or experience, and it doesn't look like it really relates to engineering or physics. So it looks a little more mathematical all the way. Then comes the question that depending upon the performance of those signal part of it, signal generation, signal filtering, signal amplification, reception, detection, you get to see the role of devices, active devices that they play, and the limitations of their non-linearities and stuff of that kind can impose. So since all that gets covered as part of that theory of, you can call it microwave signal processing as far as I'm concerned, that should suffice. So with that, you get to see what kind of constraints or restraints it will put on devices and how those devices can be realized. So then there should be maybe 2 courses that deal with devices. So devices based on vacuum technologies and devices based on semiconductor technologies. And the design principles of those devices and some amount of optimization of device performance of that. The devices labs are not easy to get, but maybe there could be visits or something that show students the devices and some measurements on the devices, including all those parameters of devices that have a direct bearing on the performance of the signal processing component, start from signal generation to ultimate signal detection with intermediate signal transmission. So I think that again would make the students feel that the whole thing is integrated. Then comes the question of device technologies. And that's, of course, the most difficult part because that's the costliest part. So once again, there could be a course, at least one course, which covers, or if possible, 2 courses, but that should cover the technological aspects involved in terms of the materials, their processing and assembling into device measurements. So for vacuum-based microelectronic device or vacuum-based microwave devices and semiconductor-based micro devices. So these, I understand that obviously not everybody will be able to be hands-on with technologies, and that's to be accepted. But a week's visit, a few days visit, demonstration of the devices, some measurements on there, demonstration of the technological steps that are involved in fabricating those devices, and in particular, all the device characteristics, which are extremely important for application in signals part, that should be covered. And then there ought to be a course on traditional materials and novel materials and material characterization. So traditional materials, of course, you have different materials that go into making of devices and systems. So material characteristics of those materials in terms of requirements of material perfection or control of material parameters and their influence on device performance, and some of the techniques which are used for making the material. Also the novel materials like metamaterials, where you can tune in the quadrants of epsilon and mu. So that would be to me a postgraduate program that covers this part. Then there should be at least, I believe, 2 courses can cover the other application parts that are other than purely communication, multimedia, voice, data, whatever. So there could be a specialized elective on radar signal processing, which is becoming extremely important, and students can now be brought to understand that all this connected car business and self-driven cars, self-driving cars, how they use and leverage the microwave and millimeter wave technologies to really perform the function they do. That all the artificial intelligence or whatever else you do sits on top of that. But these are the basic sensors as well as the basic connection medium. So that kind of a, those applications which are not, let's say, traditional XG, 2G, 3G, 4G kind of communication applications. So they should be called. And applications of microwaves in remote sensing applications, applications of microwave in civilian security applications, applications of microwave in a very, very promising field which is coming up is drone swarms. That's an extremely important area that the national securities are really going to pursue hard. So a swarm of drones is something which is cheap. Now that's the equivalent of a cheap device, a comparatively cheaper device, less detectable, being made more deadly, and working in a huge coordination. So I know of efforts where drones in swarms of as large as 5,000 are being researched by people. Now, how much is the communication among them? How much is the sensing part that is involved there? All of that is really, it utilizes microwave technologies largely. So issues of that kind should be also brought in applications, plus the industrial sector and also these green chemistry, microwave enhanced chemistry and chemical engineering. So one application side, some of these areas should be taught. I believe all of that, and of course, IoT, which everybody youngster today gets fascinated by IoT, but what lies in IoT, particularly the sensing part and the communication part. The sensing part, of course, will have also non-microwave type of sensors too, but the communication part is again totally RF and microwaves. So these are technologies that will excite students. Unfortunately, the communication industry in the country is more, field deployment oriented, and it does not therefore excite engineers too much. But I believe that there would be a requirement for developing these technologies, as we would be seen to be more attractive because of government policies, and more able to support them because of the availability of high quality trained engineers. So it is from that viewpoint that I believe that microwave, call them, I don't know how to phrase it. If you simply call them microwave postgraduate courses, probably the students would not be attracted, because they will still have, the old labeling of microwave being just electromagnetic theory being carried forward would be there. But advanced systems for communication and security, or advanced systems for communication, communication and probably security could be the kind of topic, or one could think of a better topic. I'm saying it more often. And with this kind of content, so you will have a master's degree students who would be well versed at least in the basic concepts, and thereafter he can go and work in either very high power microwave tubes and microwave devices required for plasma fusion applications, or for let's say radiation machine powering, or screening applications and stuff of that kind. So, but he would have a broader base. So he could also move into, depending upon his interest and employment, the basic level of employability would be wider. With concomitant, which I hope would happen, emergence of design and development of active microwave devices and systems based on them in the country in the same way as it has happened in some other areas. And so there would be more, hopefully, hardware design and development. Right now, most communication that is being developed in the country is really communication software. So hardware, but I have reason to believe from what I now try to, from what the signals come, that I think the moment is becoming opportune for taking up the communication hardware design, development, and production in the country. So I thought that would be a way where we can possibly sound out trying to do a undergraduate vertical. These days, I know many colleges have started minors. So one way to look at it is that a minor is worked out, but I feel that a good quality postgraduate program with this width would leave a student pretty employable in the current employment situation also. And I have reason to be assured that the employment situation is going to be significantly, if not entirely drastically better in coming years. So with that sort of thing, I would say that we could possibly debate or discuss on that kind of a curriculum and figure out. To me, somewhere like 8 courses would be required to make a person widely employable, so that he doesn't face the specter of unemployment after having done a very rigorous course program. And to that extent, probably a master's degree program or a graduate level program. But as I said, it cannot be only on devices. It cannot be only on communication. It has to holistically handle everything where microwaves, millimeter waves, terahertz eventually, and even RF, they find applications. And that, to me, could be something that fits a student's requirement of a job and interest, dovetailing of interest beginning from an introduction, going all the way, ending at the materials. So I think I would conclude with that. Thank you.
Thank you very much, sir. I am sure what you have mentioned would help us when the position paper on microwave is finally taking shape. And what you have mentioned will resonate with several of the panelists as well as attendees. I'll just, in the interest of time, probably take one very quick comment or questions, if any, from the panelists.
Am I audible? May I ask a question? I'm BN Vasu speaking.
Yes, sir.
Sure.
I can speak?
Yes.
Okay. So, thank you, Dr. Chandrasekhar. You have very nicely given the point that the course should be named after some sort of applications. Maybe it could be RF communication system or microwave communication systems and applications. Systems should attract the person very well. Now, I could not understand what is the meaning of IoT.
Internet of Things, Dr.
Okay, but see, there is a reason why I am asking you.
Yeah.
IoT stands for inductive output tube. Now this has been
that's true. So that's for the esoteric community.
Dr. Kumar is sitting there, ex-director of Microwave Tube Research Center. Okay, while I would like to comment one important thing. Dr. Shivgaonkar, Professor Shivgaonkar, has given a picture of what is going on in the country in the area of microwaves and something. But I found that the name of IIT VHU was missing. I must tell that IIT VHU is also doing some work in the area of microwave tubes. And also IIT Roorkee started some work, and some students are still working there. Some places like VIT, Vellore Institute of Technology, Chennai, they have also started some work in microwave tubes. And I would like to point out that there are some universities elsewhere outside the country where there is a department like electromagnetic engineering, where electrical machine is taught and antenna is also taught. One example I can say, in 1990s, I have seen myself in Imperial College, London. There is a department called electromagnetic engineering, where same thing, electrical machines is being taught and antenna research is also going on. So this electromagnetic theory has to be tacitly absorbed in the name of the course. See, RF can include microwave, millimeter wave, definitely one can interpret. So it could be as suggested by, as pointed out or hinted by Dr. Chandrasekhar, the course should be not something like electromagnetic or microwave. It could be RF communication systems or something like that. Or one can think about it. Thank you very much. Thank you.
Thank you, sir. Thank you. Thank you, Vasu sir, for your comments, and Chandrasekhar sir for your brief talk on prospective curriculum changes in general for microwave. Now, moving ahead, we would like to go to the next session, and I would invite Professor Subramaniam to please address the audience. Professor Subramaniam is teaching since more than last 25 years in IIT Madras in the Department of Physics and has worked in the area of microwave and photonics. His current interests are working in EM shielding, energy harvesting, and terahertz technology. So with this brief introduction, I would invite Professor Subramaniam to please take over. Professor Subramaniam, can you? Yeah.
I'm sharing. Are you able to see the screen?
Not yet, sir.
Taking time for sharing. It's taking time for sharing. Please wait. I think it is still circling.
Yeah.
Professor Subramaniam, I wish to especially welcome you. I have heard a lot about you, but we never met.
Yes.
We would like you to participate with our group more intensively in future. And I request the same thing from Professor Shivgaonkar also.
Small problem in
and all the next speakers, other speakers as well.
There's a small problem in sharing. I think it is simply saying connecting. Are you able to hear me?
Yes, we are able to hear.
Are you able to hear me?
Yes.
Okay. I think the sharing is having some problem. It is rotating. Okay. I'm closing it and then I'm trying to open it once again. Please. Sorry for the delay.
Sir, now we can see your screen.
Yeah, yes, okay. Because there is a problem in the, I think I had two screens maybe.
Okay,
So
okay.
let me, okay, are you able to see my presentation now?
No, we are seeing the WebEx window. Yeah.
WebEx window.
Yeah, now the
Still
presentation
I am putting it.
briefly.
I think there is a small delay happening.
Okay.
It is, now is it okay? No. No, are you able to see that screen?
Yes, the PowerPoint has come in.
You have to
So
make it full screen.
yes.
PowerPoint. Okay, then I will go to PowerPoint and do it. Okay, I will
Yes.
I'll take the PowerPoint. Yes, is it okay now? Okay, is it okay now?
Yes, there is a slight delay, but yeah, it's okay now, sir. If you can please.
I am just moving the slides. I'll go for the full screen.
Yes.
Okay. It is, if I move this screen, are you able to see the change in the slide?
Now we are seeing slide number.
The slide 2. Okay, fine, fine.
Yeah.
Okay, so good afternoon, everyone. Okay, I thank Professor Lalit Kumar and Professor Surendra Pal for inviting me. I also thank the committee members in this particular regard. I also welcome all the participants. Okay, so I feel like something like I am a Maruti car in big trucks, 24-wheel trucks in BTV. Okay, you are all very high in the stalwarts in microwave, and I am going to be something like a kind of a physics person among the engineering people. Okay, so Professor Shivagankar actually has taken almost all the things what I'm supposed to, or I planned to give. Okay, he has told many things about the happenings within the within India. Okay, so I thank Professor Shivagankar for sparing the time from my thing. Okay, and I also would like to thank Professor Surendra Pal for suggesting that he wanted to have 2 courses. Okay, anyway, I will come to that. Why I want to have more than 2 courses, or I will come to that further discussion a little bit later. Okay. Why we are going to have this meeting? You know very well that the applications for the microwave, millimeter, terahertz, they are all going to be expanding enormously. Even though all these 3 regions, if you see that the devices are, they have the same name. They can say filter, there also will be filter. Okay, there will be polarizer, there also there will be polarizer. But then the architectures are entirely different. Therefore, when the architectures are entirely different, one has to work or one has to teach the students in a different way. Okay. So like, amplifiers, detectors, sources, antennas, beam shapers, all these things will have different architectures, and therefore not a single methodology will be helpful to them. So we may have to actually span the whole region and do it. Not only that, the materials what we use for these frequency regions are entirely different. One maybe we may be using only the FR4 substrates or Rogers substrates for the microwave, but for millimeter wave we may have to make our own substrates for them. In terahertz, most of the time they use only the silicon or gallium oxide substrate for that. Okay. So our material science is now getting integrated into the system. So without material science, our flow towards the terahertz will not work. Another thing is the terahertz, when you go, you will have to have the spectroscopic studies. So whenever you are having the spectroscopic studies, it gives a kind of a full information on that. So this will give you how one can utilize the material, and also how one can actually characterize the material. Both are going to be very much useful for the devices. So then you are having full wave simulations, which are all now abundantly available. Okay, but then fabrication methods are going to be entirely different. Okay, it is not simply taking a PCB type and then doing it. Now the fabrication methodologies are going to be very vast, right from the regular microwave to that of the nanometer level fabrication. Okay, so with this very large change, the students know they have to choose where to go and then how to do that. I now request all, in case you have any trouble in the viewing or in the my voice, okay, please inform me, okay, because I'm not able to see you all. Okay, now what is that basic thing we can do for the students? It is that we have to strengthen the academic setup. So that is the first problem we have to make it, because students are not joining up. Another one is, if the students are joining and then they complete the course, where they will go? So one has to increase the Make in India industries. So that is another important thing. Now the industry's growth depends on the growth depends on the user base. So the user base is more, then naturally the industries will grow. Once the industries grow, then you will have the need for the students to be more. Once the need for the students to be more, the academic setup will be automatically be strengthened. Okay. So India, yes, now has academic industry setup. Okay. We have the Make in India concept along with the programs. Many programs are there. One of the programs is UAY. Okay. That is one such project example where we have the industry academic partnership. Okay. There we can actually work on developing new products in that. So if you see the IITs, all the IITs are now having the research parts to encourage such a newer partnership in that. So if we take this, sorry. So if you take this academic setup, once the academic setup is there, there will be teachers and there will be students community. Okay, then these two people will be contributing to the industry. The industry will follow the user group. The user group will give the input to the industry. The industry will give input to the academic institution, and then academic people will try to modify the curriculum so that it can follow along with the students. So this is how the idea or the methodology generally works. So here the problem is that we don't have the enormous number of industries. The microwave terahertz industries are very less. Naturally, this may be due to the very limited consumers, as Professor Shubhankar also mentioned. Who are all the users? Users are going to be DRDO. So most of the times the industry comes within the DRDO setup itself. And another one is lack of human resources. People who are all joining this DRDO, they don't complete the whole course and then do that. So their practical experience becomes much more useful to them rather than by using the theoretical concepts of that. Another thing is academicians. So if you see the academicians, they also should not only be good teachers, they also should be good pseudo-industrialists. That means they are not industrialists, but they have to behave like an industrialist. So with that, I think they will be able to give a kind of a setup to us. Okay. So what are the things to be done? As Professor Santrasekhar pointed out, that in the 12th standard and 11th standard, how to give the information. It is there available. Presently, it is in a very low level, no doubt. So it is in the physics. If you see that physics secondary, higher secondary education, we have the communication system in the 10th chapter going on. Okay. So it is in the Tamil Nadu NCERT book. The same thing also, some Tamil Nadu textbook, the same thing also can be seen in the NCERT book. Only problem is the NCERT book stops with the communication system, whereas the Tamil Nadu government also tells you something about the radar. Okay. So now the one has to modify the course curriculum. So why we have to modify the course curriculum? It should include modern topics. That means the course curriculum, generally what we do is the course curriculum will be always revised every few years depending on the need. So whether if it is IITs, NITs, maybe it is easier to do, but whereas in the case of the universities and other engineering colleges, it will be very difficult to do. So here we can include the modern topics, the current technology with applications for industry as well as the academic people. Okay. Okay. Now another thing is that what about the laboratory classes? As Professor Chandrasekhar pointed out, that laboratory classes should be having a kind of a hands-on experience. So here also, I agree with him that we should have a virtual lab with full-based simulations. Okay. And then when they say hybrid lab class, okay, here we need to have a kind of a virtual lab also along with the physical lab. That's what I mean by the hybrid classes. Okay. So one has to put a hands-on experience on everything. Okay. So and also the special labs we should have. That means if I take a kind of a few institutions together, okay, we can have a kind of a laboratory, teaching laboratory, where the students can go and then actually work on that. So that gives you a kind of a special group. Okay, special need it can do. Now, nowadays, we have the DST program called SATI. Okay, the SATI program will be able to give such a kind of a thing, but that is mainly meant for research level. Whereas this what I mean is that we certain special measurements or special lab classes can be put in the combined way. So in this particular aspect, one has to have an interaction among the nearest institutions so that they can share the something like crowdsourcing, you can say. They can share the resources. So the money also will not be that much high. So another thing is that can we introduce EM and the microwave at class 12 and 11? So as I mentioned that it is there. But problem is that nobody asks questions in JEE. First of all, if you are going to do anything on 11th and 12th curriculum, you should also check into the JEE questions. What is the JEE syllabus says? So that's what people will be able to concentrate on that. Okay, not the other one. They are not interested. Most of the 11th and 12th students are not interested just for learning things, except few. Okay, for others, yes, it is mainly meant for the JEE or for the NEET coaching. Anyhow, NEET coaching we can remove, okay, because JEE is what is important for the engineering things. Okay, so the syllabus is not generally covered under JEE. So if there is a scope for covering it under JEE, yes, then there will be a serious effort to put that. So what in few years back, if you remember, or if you, for the information, you will like to tell that, for a few years before, JEE had only done by IITs. Okay, during that time, the paper was done such a way that we give modern topic, okay, as a kind of a paragraph. As soon as you put a paragraph, the students will read the paragraph, understand that, and then they will they will actually answer the questions given to them. It's like a paragraph style. Okay. So there, we put something like, what is the photonic results, negative refraction, all that, we can incorporate into that, and then we did that. If I remember that, there was one year where this particular question was asked about the negative refractive index. Okay. So that way, one will be able to give a kind of a thing, but unless otherwise it is covered under JEE syllabus, it will be much difficult for us to make them understand that. Okay. So final part is that cloud sourcing, okay, that has to be method. With that, cloud sourcing is very useful for fabrication methodology, because fabrication is a very costly affair. So one institute alone cannot pay. Okay. So the Center of Excellence is what they prepare. They have to help us, help others also to on a sharing mode to fabricate the things. So that this also will be very much useful for research scholars as well as for the PG students who would like to do the project work. So that will give them a kind of a higher exposure. So then what about our academic responsibility? So being an academician, we should have a certain responsibility on that. Okay. Now, whenever say the academic responsibility, I put it on the teacher. Our teachers are very good, no doubt about that. Okay. Our students are so good. They are very nice. Okay. And that is also no problems in that. Okay. Then what is lacking behind? Why people are not coming? As Professor Shivgaonkar as well as Professor Chandrasekhar pointed out, it is the, first of all, it is the where interest has to be taken. And some of the comments also I have seen that the students are not interested to do that. Why? Okay. All these things come under the responsibility of the teacher. Okay. Maybe getting the job may not be the responsibility of the teacher, but giving them the interest in getting the subject is the responsibility of the teacher. So whenever I have taken a kind of the course called electromagnetics and applications, okay, I always give a kind of an applications with the demonstrations, etc. Such a way that at least one student will come and then ask for a project work. Okay, in that particular EM work, what we do. So this is the thing what the SATI program gives you, as in that earlier view graph I have mentioned that. Okay, so that gives you a kind of collaborative nature of that. Okay, that way will come. So the teachers are going to be the backbone for the student as well as the research community. Okay, there are two kinds of teachers, I will say. One is the conventionally recruited, like complete PG, they have complete PhD, they complete PDF and come for the teaching. Another one is called lateral entry teachers. Yeah, lateral entry teachers are something like 40, 50 years old. Okay, they would have done this PG and but they would have joined either with the PhD or without PhD, they would have joined the R&D industry. Now they can also come to the teaching. As per the new IIT regulations, okay, they have the, if they are having the experience, relevant experience, they will also be able to come as a teacher. near equivalent level in that. So this is called lateral entry. Okay, both the teachers, they have to have the continuous knowledge update. So they have to either attend the short-term courses or collaborating with the neighboring institutes, like using the SATI program, and floating and participating in conference, so that the students will be able to have an awareness of that. Once the teachers know they are involved in that, students will have definitely the awareness on that, and then they will try to participate in the conferences. So once the teacher is floating the conference, students will automatically be part of that. Okay. Another one is, recently we have seen that I am also in that RF and microwave group, okay, in the WhatsApp. So these type of groups are very much active, and many such groups will be helpful to the students to clear their doubts as well as getting the help, etc. Okay, so this type of social media platform is going to be very essential. If I remember that in 2003, when I started this photonic crystal group, okay, there was only one email group available. At that time, no mobile phones were not there much. So we were using only the email group, and then one website was there. So there we'll go and then actually have an interaction. Okay. So from India, I think myself and Professor Radha of IIT Kanpur were there. And that time she was in IIT Bombay. Okay. So most of the people not were only our students were there. So very limited things were there. But whereas now I see very nice way of interaction through the social media platform. Okay. Next thing is teaching style. So how to have the teaching style without compromising the theory critical part of that. So generally what we do is we can actually do the basic theory, okay, but then most of the times you make it a kind of a demonstration or visualization. Once you do the demonstration or the visualization, okay, then automatically people will get interested into that. Okay, so this will be giving you the kind of an addition to that of the hands-on experience through the lab classes. Okay. Now another one is that one can also invite experts from that. So generally what we do, we invite experts, okay, and then ask them to deliver a talk about how they have actually their research and R&D work is going on, etc. So this must be a part of the coursework. Okay. So here also, depending on whether it is for RF means we take the local RF industry person, or from Samir we can call, and then they will be able to give. Okay. So another thing is that involving the research students in involving the regular BTech or MTech students in the research project. So we may have a research project. It's not only for money, okay, but it's also for the to give them what we do, so that they will be able to get interested in that and then start working on that. So this way, I feel that one will be able to motivate. Okay. Now, when I told about the conventional teachers and lateral entry teachers, okay, what is their difference? Say that conventional teachers, they are generally will give more theoretical derivations because they were trained, or they are trained to do that. Okay, like right from the multiple expansion. If I ask me to start, I will start from the beginning and then go on deriving it till the final end. Okay, so now that becomes a kind of a boring. Sometimes boundary conditions. All these things will be becoming a boring aspect of that. But as a regular teacher, okay, as conventional teacher, we'll be trained to do that. So we tell the students that yes, from this we start doing it. But this will be a little bit problem for them. Okay, so naturally, so one has to have a little bit. Instead, we can put the final expression and say that. Okay, but we are not, as a conventional teachers, we may not be having that experience in that. Okay. Another thing is examinations. And when we do the examinations, we always give based on the mathematical descriptions, etc. So, okay, like something like, and these examinations, we see that most of them are going to be infinitely long, spherical, all these things. Okay, that tests the mathematics skill rather than that of the understanding subject. So it is better to have more of the conceptual based questions rather than the mathematical based things. Okay, mathematics is there, no doubt about that. We cannot actually avoid mathematics. The thing is that can be a little bit, whereas your answering questions can be on the conceptual based ones. Okay. Now, what about the lateral entry teachers? They are coming from an entirely different background. They know all the case studies what they have done. They know how the research is means actual work has been done in the practical field. Therefore, they will know when they teach, their methodology of teaching is entirely different. So we also need such teachers, okay, who can actually motivate more on students. Okay. So here in the teaching community, at least 10% should have that lateral entry teachers. And if possible, in your course, Okay, you can take help of the LET, means lateral entry teacher, if at all they are available, to give a kind of their experience on that. Okay. So what would be the advantage if you have, if you embed this teachers, two kind of teachers here, they will have the new outlook, okay, and outlook to students towards the practical situation. So how it is happening, etc. Okay, what about the student perspective? So as a student, what will I have? I would like to have more on the practical or application point of view, as long as it does not hamper me, okay, in getting good grades. Means if you may give a lot of application point of view, but in the question, if you ask theory, what will he do? So it is of no use. So therefore, whether the coursework or the teacher, the responsibility of the teacher, whatever be the coursework, the responsibility of the teacher is to have a kind of an application point of view added to that, okay, along with the theoretical part. Okay, so they have to ensure that that does not hamper that. Another one is a combination of case studies with theoretical background. So students will like to have, okay, what about the case studies, right? In case you are saying about the radar, how fast we can detect it, why you should have a very sharp pulse, okay, what should be the turnaround time, and why the turnaround time is important. All these things now you give with the case studies into that. You how the speed of Tejas, etc., or a Rafale, how it can be used. All these things when you give, they get more interesting in that, and then they do that. Most of the times we follow that particular thing in our IITs. Okay. Another thing is demonstration. So demonstration is very, very important. Even though we do the theoretical course, even in our theoretical course, I generally teach this PH 5590 microwave physics, where I do not forget to give them demonstration. Demonstration can even be something starting from like a, how skin depth can be demonstrated, okay, and then also the photonic itself, how one can use it to demonstrate. All these things can be done. Even I have shown once how impedance matching can be done, okay, in a live way. So therefore, this actually makes them more interesting in the particular subject. Some of them know they have worked on defense, and when they see how the impedance matching is being done very nicely, they will be having they will be actually have a attachment towards the theoretical part of that, because that is what is going to give more on that. Okay, so so therefore, what I say, the lab classes for simulations, what you have separately, you can actually integrate it with the theoretical class. Okay? So along with the theory, you also take the component for your simulations. There in the classroom itself, when you start doing the live simulation, they will be having more interesting thing in that. Okay. Okay. So another important factor is that whenever a teacher completes that, okay, what the students would like to see that last few minutes, if you are able to, or initially you tell something about applications on that or the latest trends, it will be actually motivated. The student also will be liking that. Okay, so that's the kind of the student perspective on that. Another thing is that shall we give the freedom to the teachers? Yes, NITs and IITs, they give freedom to the teacher, okay, to modify from the approved syllabus to include modern topics. So there is no need for them to have any curriculum revision unless otherwise there are many teachers, okay, they are teaching that time curriculum revision and an official mode it has to be. Otherwise, you can have an unofficial mode on that. Okay. Therefore, here you can actually tweak the subject, okay, and then include that. Even though we have the microwave courses, etc., may not include this photonic crystal, but then metamaterials. But then nowadays we need without metamaterial photonic crystal, nothing can be done. Okay, something like conventional antennas will be there. So you can teach them, and then by doing that. Not only that, materials also is going to be very important. So you can tell them that materials part also a little bit on that, add it up, like in that case of the spectroscopy. So this will be able to give. Therefore, since even though your course structure may not have a demonstration or simulations, please include them into that so that students will be able to have that. So this is the freedom given to the teachers, okay. And then if you are there from an IIT, then, but I do not, maybe all the private in the institutions, autonomous institutions also, they may have the freedom to choose that. If that is the case, please add the demonstration as well as the simulations. If possible, also add this mini projects to boost their interest. Okay. Okay. So what are the topics? Okay. Mathematics is essential part of the engineering. Okay. So that cannot be removed from that. Okay. So that is the thing. Only one thing we can say that for undergraduate, yes, you have a rigorous mathematics you can do because of the basic mathematical procedures. But when it comes to the PG category, okay, you can have the final derivation, so that you can have only very less amount of mathematics, but more on the description can be done. Okay. But another thing is that your EM, okay, electromagnetism can be taught in different ways depending on the perspective of the application. If the perspective of the application is different, okay, this can have different ways of doing it. Okay. Okay, so this is because your EM electromagnetics, okay, in physics, if you see, deeply involves the theoretical framework, which is common for all the frequency bands. Okay, but as soon as you are having this application point, depending on the interest, okay, this splits into several aspects, like RF part separately, microwave part separately, IR and optical. Where in IR and optical, people don't bother about the magnetic part, whereas RF and microwave, we need to know about the functional materials, okay, like ferromagnets and ferroelectrics, etc. Okay, so in the existing curriculum and what to be added. Okay, now if you see certain IITs, okay, if you see certain, you have more on the communication technology. I have seen certain IITs where they have courses more on the communication technology. That includes a kind of an RF systems lab also, and also the RF field teaching. But what I say is that it is not enough to have only one course, not even two courses, but you have a variety of courses. Okay? The variety of courses will be, that means you can float a MTech curriculum itself, something you have MTech program for RF and microwave. You can say RF program on microwaves and terahertz derivation. You can have that, which can cover, as far as in my personal view, you can see that can cover the mathematical methodologies, okay, and then simulations. In the case of the numerical techniques of simulation, separate as a course. Okay, mathematical methods as the basics, as a slightly advanced level, as a course you can have that. Then propagation studies is becoming very important, because whenever you are having communication, you have the multi-parts and and all these things will be there. So that propagation studies is going to be important. Then you are having the passive as well as active devices. It's not a single course. You can have multiple courses on that. Okay. Then you are naturally you have to have a fabrication methodologies. So that has to be another course separately on that, because you have varieties of fabrication methods. Then you are having the materials for electromagnetics. That means that nowadays we are not having simply, as I mentioned, the PCB type of materials, but we are having this multifunctional materials where one can tune it, etc., using the external things. Not only that, one can have a wearable things. Therefore, these multifunctional materials will be very much useful to you. Okay. Another thing is that we are not having if I say photonic crystals, metamaterials also a second point of that course for that, which would be useful for them to design the antennas and other aspects of that. Another thing is imaging aspects of EM, which I think not a single course is being it's very rarely being covered in any of the RF syllabuses. Okay, so it is better to use these imaging aspects of EM. You can have a passive as well as the active imaging, which are all not, which is then you are having the super resolution algorithm, the image processing, all these things will be there. So that itself as a thing, as a course. So what are the applications of the imaging you can take it? Like one can have imaging for the security purposes, imaging for your non-test evaluation. Therefore, that itself as a course you can have. Then for microwaves as well as millimeter waves and on terahertz, you can have the spectroscopic studies on the materials. Because without materials, our future is not going to be whatever be the application you are doing. You have to develop the devices, and therefore spectroscopic studies on the materials is going to be very important. So here you can see that vibrational spectroscopy as well as the rotational spectroscopy, both can be used in that, and then to study the whole thing. Okay, so wherever you are going to have that 140 gigahertz for ozone detection, or for the 94 gigahertz for imaging, or for 600 gigahertz for the carbon monoxide, etc., you will be able to use this particular spectroscopic studies to actually decide the application point. Then naturally, all your star.gs are there, means communication aspects are there. Apart from that, you have to have the labs, which is supposed to be RF labs, plus simulation labs you should have. Then your industrial R&D seminar, it's a must. Okay, one has to have the periodic industrial and R&D seminar throughout the semester or throughout the whole curriculum. I say entire program itself will say that. Okay, generally you have that projects which will be there. And right side here, I have given you kind of a course which is taken from our IIT electrical engineering department. But this is, I think, in my personal thing, it may not be that good. In there are 8 students working, joining this particular course every year. Okay. So what about the practical classes and lab classes? The conventional classes, lab classes, they actually purchase standard circuitry. I have seen certain places where no, there's a board available and simply they connect it and then demonstrate the filters and other things. Okay, so that may be very much useful for certain low standard or okay, initially you can give that, but then it is better to have a modified lab, and that actually forces them to think about the problem and design. Assume that you want to have a filter, you want to design filter, don't give them standard filter, but let them go and see the textbooks and then design their filters and then fabricate it if possible and then do the experiment. At least they can do the simulation after seeing the gist of actually taking a standard filter and doing that. But once they are using a standard filter, you can ask them to actually use the standard filter and then see how the selectivity in a receiver should be. So that way, they can actually modify the lab syllabus, okay, lab experiments such a way that they think and then do the problem rather than simply putting it in circuit. The students also will have to, if they are given a kind of a responsibility that they should think and do that, they will be very happy to do that. And if possible, we can have a very small active components that can be made. Okay, a simple diode based detection, which is available for around 1,500 rupees per detector. Now one can make it. You can actually take it and then fabricate it, do it as a kind of 2 or 3 people together will be doing it. Next week, another group of people will do it, etc. So that way, one will be able to give a kind of a exposure to them, and when they see that they are able to detect the microwaves, okay, from using their own how they are soldered and other things, designed how they designed that, they will be very happy to do that. Okay, in the research level, okay, what is to be done? Okay, this is research level. Okay, you have to have many things like very well for communication purposes, filters are there, antennas are there, all sorts of antennas are there with or without metamaterial. Okay, or is it tunable, non-tunable? All these things will be there. Okay, and then but then it's also very important to see, because many of the papers from India, I see that they all work on the antennas. Okay, but many other people are not working on imaging aspects. So these are all the things I think, but I have seen that for some of the registered participants, they are working on imaging, okay, and then also for energy transfer, I have seen them working on that, and then some 1 or 2 I have seen on the health aspect. So imaging aspects, okay, then beam shaping for energy transfer, the power, they say energy harvesting, but what I say is not energy harvesting, where the energy transfer from one location to another location, apart from energy transferring, energy storage, okay, or energy harvesting. Then also the people have not studied on novel materials for substrates, okay, and because when I say that novel materials for substrates, it will be very much useful for them to tune your dielectric as well as magnetic properties, so that you will be able to control your antenna characteristics or something like that. Not only that, we should also have develop a new sensor. Maybe after Dr. Jagdish Chandra Bose, I think we have not developed a very large number of sensors into that, even for millimeter wave, etc. So it is better to develop new sensors, maybe, and then also the health aspects of the microwave, which we have not studied much on that. Okay, even though you have studied a little bit, okay, it is not enough, I say that. And okay, so that is very important on that. Then your research level, one has to have a focused teams. Unlike other conferences and then workshops, where you have a broadband level, okay, broad level it can have, and then there are around 150 to 170 participants, and it becomes a mela. So it is better to avoid that and say that it must have a focused theme. Once you have focused theme only for people, maybe around 30 to 40 people, but they will be having a focus to work on that, so that they will have a more on their collaboration can also be included into that. So that way, India, we can actually have a kind of a group which can actually have an exchange of thoughts on the scientific manner. Okay. Okay. Another thing is that since no single institute can have a large amount of funding for that, okay, it is better to have a collaborative proposal, okay, which is very lacking behind that nowadays. Okay, everybody, we are all know that everyone is very powerful, everyone is knowledgeable, everyone has a expert thinking, but none of them, okay, they actually join together. Now recently I have seen that one of the SATI proposal, okay, which has been sent out by the DST. I think people are these type of the proposals give a kind of an opportunity for them. Even if I understand that NIT Trichy also tries to have a kind of a one particular proposal happening. SSN has another one like that. So a few many groups, even IIIT DM is also going to be part of that. So this will be giving you a kind of a focus on many aspects. So that also will help the students to achieve their goals into that. Once the students are more, once the manpower is going to be more and more, okay, then automatically our industry entrepreneurship things also will be getting higher and higher. Okay. So what is the final roadmap of that? The final roadmap is that now our immediate goal we can have long-term goals. Immediate goal is that we can have specific themes, okay, and then for the funding and collaboration, that can be on the communication systems, one can be on the integrated imaging system for security purpose environment, one can be on the shielding from electronic bombs, okay, and then for anti-personnel EM guns. This is all something I have given you a kind of a tentative things, okay, spectroscopy. All these things now you can have a expert group, because INA expert group is there. Similar way, they can actually form a kind of an expert group where now people can join together and then look for a collaborative proposal and for a targeted delivery for that. Okay. The long-term goal, yes, we should have a cloud-based research environment. We should be able to generate a kind of the HNI, say somewhere Hyderabad. Like that, you will be able to create a kind of a center, okay, where the common things can be there. It's a kind of a cloud-based research environment can be there. Okay. Another one is that must be academic industry environment, which it has to have for the Make in India manufacturing facilities for passive as well as active devices. If you see that IPR Ahmedabad is is very much working on high power devices and also on higher frequency devices, but they have to import. Okay, that's a sad part of that. Okay, why can't we have the Make in India facilities in that? Problem is that even though the number of users are going to be less, it is better to create a kind of a facility. So finally, what we do in our micro lab, we do it on propagation aspects of photonic crystals. That has a impedance variation with the time. It is not spatially periodic, but also the time periodic in that. We also work on chiral metamaterials, okay, leading to topological photonic crystals. We work on near field imaging based characterization for NDs. We also work on FMR based micro devices and fundamental studies on spin waves for the memory as well as for switching applications at micro frequencies, and millimeter wave based absorbers, polarization converters, and sensors. We do that for metamaterial based absorbers, polarization converters, and sensors. We also work on new composite materials that can actually replace the commercial substrates for many applications. Okay. So with this, my final takeaway, we should have a modified curriculum that should include industrial interactions. And the courses should be in hybrid mode. Should not have only problem sheets, but also demonstrations. Lab courses should not merely be a connect and get the result category, but it should involve hands-on experience. Microwave terahertz involve different aspects to be discussed. So depending on the need, course content should vary. And then interdisciplinary is becoming a very important, because material science and the electron magnetic people, they have to come together. And with this, I thank the INAE expert group, Professor Surendra Pal and Professor Lalit Kumar, okay, for giving me an opportunity, okay, to deliver this particular small discussion topic. Thanks a lot. Any questions I would like to answer?
Thank you, sir, for your talk and for raising many important teaching learning related issues in microwave engineering. Maybe I'll take any comment or questions from this.
Surendra Pal is in mute.
Yeah, Pal sir, Dr. Surendra Pal sir, I think you're muted, sir, if you're speaking. Sir, we are still not able to hear you.
Yes, we are not able to hear you, Professor. No, it's still we are not able to hear. I think probably we may have to talk over phone like a regular.
No, sir, still we are not able to hear.
Maybe, sir, you have to remove the headphone. No.
Take out the jack. No.
Still no, sir.
Technology problem.
Sir, now it's audible, I think. Can you speak?
Now, am I audible?
Yes, sir, you're audible, sir.
Okay. Thanks, Dr. Dixit. We will have to maintain some time because we have to finish the thing. We have 2 more speakers.
Yes,
so thank you, Professor Subramaniam. If we, you can send this to Raji or Professor Dixit, and then we'll put in our term paper, which we are preparing, and then we'll circulate it to everybody.
Yes, sir.
Okay, go ahead.
Yeah, so our next speaker is Professor Subalkar, and I would request Professor Jalil Akhtar to kindly please welcome him and introduce him. Professor Akhtar.
Thank you. Thanks a lot. So it's my pleasure to welcome Professor Shubhal Kaur to this list of speakers. So I think Professor Kaur is well known in the RF academic field. He has been working for many years. He has been head and professor with the Institute of Radio Physics and Electronics, Institute of Calcutta. He worked there for many years, more than 3 or 4 decades. He has around more than 100 publications. He may primarily work on impaired diodes on different aspects. He was also a scholar to Lawrence Berkeley Laboratories, US. For a few years, then he worked at a number of institutes in Kyoto University, Japan, Oxford University, and so on. He has authored a book on microwave engineering, which is, I think, quite famous. Many of them might be knowing in 2016. And so I think it's our pleasure to hear from him his aspect. So with this, I think I welcome Professor Kaur to this lecture series. Please go on, Professor Kaur. Can you share the screen, Professor Kaur, or you have some difficulty?
Yeah, I'm trying to do that, but
okay.
The screen has come. But what is the problem? So small. What is the problem? Why the screen is not becoming big, I do not understand.
I think first you can open, then probably you can try to maximize.
Entire screen. Yeah, I think now the screen is shared. Whether the screen is shared?
Not yet.
We can't see it, sir.
Okay, okay, let me see. What is the problem? Share the content. You share your screen.
Now you can open the maybe your presentation. Yes.
Is it now?
Yes,
shared?
yes.
You can take it. Yes. Thank you. Go ahead.
Now it is shared?
Yes, sir.
Okay. Thank you so much. So long I have been hearing 3 experts, and whatever they have said, they have covered everything, left nothing for me. So what am I to say? I am really confused, but I am always with the students. So whatever I will be talking at a very grassroots level, and that too for students. All right. Microwaves 300 megahertz to 300 gigahertz by all classical definitions, and even today it is accepted. Terahertz, more than 300 gigahertz, but less than 10 terahertz. 1 terahertz is 1000 gigahertz. Beginning of microwave engineering is considered to be from World War II, because then the need for radar became important and microwave engineering started developing. Research on terahertz technology started effectively from first decade of the century. Earlier it was used for astronomical studies. History of millimeter wave research goes back to the work of J.C. Bose and others around the world in 1890s. Teaching of microwave and wireless engineering started in Institute of Radio Physics and Electronics sometimes in 1940s. Now, while talking about teaching a microwave and terahertz, first question that comes is demands of today's microwave and terahertz teaching. Definitely the target products. We need the next generation microwave teachers. They are to be totally different from what we teachers were some 3 or 4 decades or 2 decades back, because very many new things are coming up in microwave engineering, including millimeter wave and terahertz. So next generation teacher has to be trained, motivated, and equipped and made capable for teaching the next generation students. Same is true for researchers in academics, scientists in R&D sectors, engineers for industry. So a very new outlook is required for this 21st century. What are the requirements for guaranteed products for these teachers, academicians, R&D scientists and industry? Clear understanding of fundamentals. I'm sorry. Yeah, clear understanding of fundamentals. By fundamentals, I mean both the physical concepts and the essential mathematics, not of more mathematics, not of lesser mathematics, but essential mathematics, without which RF, microwave, terahertz, and optical systems cannot be understood properly by students, by researchers. Design capability. This is a must in this new world. Design capability, we are normally familiar with analytical designs, but simulator-based design is the order of the day, the requirement of the day. And knowledge of application areas. If our students are not given a broad and clear scenario of the application areas, then they will not be interested in the subject. Why we are studying all these things? So application areas should be made very clear, and that should be in a very, very lucid way. We must place it before our students. But what are the lackings and gaps that we observe today? Interesting, for the last 1 decade or so, target products are decreasing. We all will agree to that. Reason? Many academic institutions, in many academic institutions, microwave engineering has been made elective. Very, very unfortunate. I do not know how could they think about that. Requirement for guaranteed products is mismanaged. Yes, these days, software skill, computers, and these things are definitely required.
Listen to others also, no?
Hello. But in the name of this computer literacy, we should not mismanage the whole curriculum, so that microwave, RF microwave and terahertz is not given its required place. Thus, all the sectors are getting depleted of skilled and employable microwave engineers and researchers. This is a very important point we all must ponder upon. What has to be done? Serious thoughts and efforts must be given for reorientation of syllabus, including terahertz with microwaves and its implementation in practice. Syllabus should be updated with pragmatic view in mind and scope for adding, deleting stuff as and when the time demands. Unprejudiced syllabus has to be framed keeping in mind employability and right skill development to meet the demands of microwave engineers and researchers in all the sectors. Now I will talk something about teaching of microwave engineering, and this will follow from my experience in studying undergraduate and postgraduate at IRPE for last 33 years. And while discussing this as a teacher, it will be better for me to take up a particular book and on the basis of that to talk about the possible structure of the curriculum. There are a number of good textbooks on microwave engineering written by stalwarts like R.E. Collin, D.M. Poser, and so forth. These are classical books, but the need of today is a more lucid textbook with coverage of emerging topics and simulation-based designs too. A number of new textbooks are coming up in the market. One of them may be the book authored by me, Microwave Engineering, Fundamentals, Design and Applications. It looks very odd that the speaker is taking his own book for this discussion. But just forgive me, because to discuss it, it will be better for me to take my own book, because I have written the book with certain philosophy for the future generation students. So please bear with me. While going through the contents of the book, I will indicate how the book can be used for BTech, BE, MTech, ME teaching, and also by practicing scientists and engineers. Here, emerging topics are also touched upon, which will be elaborated at the end of the presentation. Let us go through the slides. Yes, this is my book. Some of you might have seen it. I go through the contents very quickly, and I have divided in my own way what is to be taught at BTech and MTech level. Electromagnetic theory definitely should be taught at BTech level. And while teaching electromagnetic theory, which is required for RF, microwave, terahertz, optical peoples, this should be thoroughly taught. Yes, I understand that all the engineering institutions around India is having a compulsory paper on electromagnetics. That there is noise. Please unmute some of your speakers. Yeah. So electromagnetics has to be taught very seriously, but keeping in mind that we are in the 21st century. So what are the things we have to teach, with what emphasis, and what amount of mathematics we have to do, and how we can bring out the physical concepts from those mathematical analysis. So electromagnetics needs revisiting, not in the ways we were taught in our days, because there were not so much of loading of other topics on microwaves and related subjects. So this rethinking is required. In EMT, naturally, first the concept of RF comes, and high frequency behavior of transmission lines should be included in EMT at BTech level. Then guided wave structures, waveguides and cavity resonators. The field analysis starts here, and this should be done thoroughly. Whatever mathematics is required, that has to be done. because in all future studies for their research, for higher studies, students should need that capability of mathematics, essential mathematics for their further studies, further innovations, further research. So that was, in my view, EMT should have electromagnetic theory, then transmission lines and waveguides. So this should be the domain of EMT, in my view. Then comes microwave engineering, which will be a separate paper for BTech. The first thing that is required is microwave network and scattering matrix, because when any advanced microwave book is opened for its different designs, here and there a lot of scattering matrix is there. So at BTech level, they must have a good knowledge of scattering matrix for microwave network analysis. Microwave passive components. All the microwave passive components should be discussed more with physical concepts and their application viewpoints, and some of the designs. For example, I've given a design example on microstrip based directional coupler, and that design should be with simulators. Here it is done with EDA simulator. Students should have the scope to do, at least at their tutorial class, hand-on experience with these simulations. These are very simple things. These have been done by my students, and ultimately with little bit of changes here and there, I have included in the book. So it is possible with students' capability, but we have to organize our curriculum accordingly so that simulation-based design becomes a integral part of microwave engineering. Then comes impedance matching in transmission lines and waveguides. Majorly, it should be kept for advanced microwave engineering in MTech level, but some elementary things should be covered in BTech level. Again, a very important thing is Smith chart. Smith chart should be taught in EMT itself with transmission lines. And for these designs, this matching problem design, etc., Smith chart is used now and then. This is for a double stub impedance matching. And students and researchers will be ultimately working with network analyzer. And one of the options for network analyzer displays Smith chart. So when they will be using network analyzer, they must be very conversant with Smith chart so that they can very easily interpret the results. So knowledge about Smith chart, very clear knowledge of Smith chart is very much essential. Microwave filters, again for advanced microwave engineering at MTech level, but elementary things should be covered in a very judicious way by competent teachers at BTech level too. Again, all this chapter should have design problems, and that too analytical design, also must is simulator based design. Here is for low pass filter design, because these will give them the insight of the design, insight of the whole topic. They must have all this knowledge. What is this EM layout of EM simulation and all these things? They must be very, very conversant with that. I have shown only low pass filter, but simulation but designed for band pass and band stop is also given in my book. Then comes microwave tubes. Well, very often I hear from the solid state peoples that microwave tubes have become obsolete, but I don't think it's so. For high power applications, microwave tubes are there today. They will remain in years to come. Even the Stanford Linear Collider uses high power klystron as their power source. And added to that, microwave tubes are getting a new facelift with the application of metamaterial inclusions in microwave tube design, which is making them much efficient and useful for many emerging applications. So microwave tubes has to be taught at BTech level, but again with a point of caution. I remember when we were taught microwave tubes in late 1970s at IRPE, klystron and reflex klystron was taken in minimum 2 full classes. It was required at the time, but now with many other devices coming into the picture, we have to be judicious which part of the syllabus has to be taught with what emphasis. This judicious choice is very important. Otherwise, you cannot include new things. This is very, very important. What I have experienced as a teacher for so many years. Then comes solid state and quantum electronic devices. This should be primarily for advanced microwave engineering at MTech level, but some microwave flavor should be given at BTech level. I'm telling microwave flavor because all these solid state devices in most of the institutions are covered in semiconductor and solid state device classes. So here for BTech level, only microwave flavor has to be given, what I used to do in my class also. Then comes microwave oscillator, amplifier, and power combiner with solid state device, all designs, then microwave mixers. These should be kept for advanced microwave engineering MTech level. But the most important is that design with 3D field simulator of these oscillators, their bias filters, and this vector tuned oscillator. All these are to be done in the class, and these should be given as tutorial problems. There should be this simulation labs, just like circuit lab, like this lab and that lab. There should be a simulation lab dedicated for that, so that tutorial problems students can solve there. And also for more involved designs, the institutes, universities should take help of the national research institutions. As for example, from my institute, I used to send a lot of students to Samir Kolkata Center, and a number of them have gained from that, and those people are very cooperative, and I understand that all national labs will be very cooperative for nation development as a whole. Also, LNA design, very, very important for microwave designer, and that should be with simulated. They will understand how to use Smith chart, how to do impedance matching. These hand-on things are very much required. Then they will understand that what is the layout, how the final design is done by the fabricators. So all these things should be close to their heart. And power amplifier design, not only low noise amplifier, power amplifier design, all these are given in my book. Also, as a supplement to my book, there are PPTs giving the steps how to use this design problems. Then comes microwave antenna and wave propagation. Yes, with EMT, they will learn about basics of antenna, but for microwave engineers, they should also learn the specialities of microwave antennas, and that should be in microwave engineering at BTech level. Then radar and radio aids to navigation. So that should be a separate course in BTech level. Not only radar, but radio aids to navigation, that includes GPS and many other things. that has to be taught at BTech level, including some of its signal processing as mentioned by some earlier speaker. Then comes microwave measurement. Well, microwave is basically an experimental subject. So without learning microwave measurements by heart, including the fundamentals of spectrum analyzer, network analyzer, noise measurement, concept about phase noise, and so on and so forth, the learning of microwave engineering will be incomplete. So microwave measurement, both as a theoretical credit course at BTech level and dedicated experimental lab for microwave measurements, is must. Then comes microwave integrated circuit and EMI EMC. This is definitely for advanced microwave engineering MTech, but elementary things can be mentioned at BTech level. Then comes an emerging topic of microwave engineering, metamaterials and metasurfaces. Yes, I have worked on this topic since 2006, and we made the first plasmonic metamaterial in India. In collaboration with Samir Kolkata and BARC Mumbai, we have made a measurement facility at Samir Kolkata Center. And this study of metamaterials and metasurfaces by RF, microwave, terahertz, and optical peoples has become the order of the day. We cannot ignore metamaterials and metasurfaces in our syllabus. It should be, I will talk about that, how that should be exactly divided in course curriculum. It should be seriously taught at advanced microwave engineering MTech level, but elementary things need to be mentioned at BTech level. When I was a teacher at IRPE, I used to do that even at BTech level. And very brief, quickly I'm going through the difference between metamaterials and metasurfaces, because metamaterials that came from the work of Vijay Vasilago and John Pendry made the first possibility of first practical metamaterial. These are basically 3D periodic structure, and I have shown here only a 1D periodic structure of metamaterial with labyrinth resonator, a modified form of split ring resonator, and thin wires. And here is metasurface, which is not a, which is periodic among the these elements, but they are geometrically 2D structure. Geometrical 2D, but among the elements or scatterers, they are periodic in nature. They are very much important for these days microwave, especially for terahertz and optical peoples. In my book, I have given complementary split-ring resonator loaded microwave patch antenna design. I have given the details. Students should know how to make this impedance matching with Smith chart through these simulators. What is their current distributions? From that, they can understand whether the structure is at all usable or not, or what should be its polarization and all these things, whether matching has been realized. These are the design structures designed at Samir Kolkata Center. And we have seen, we have also worked with CRLH, that is based microwave filter. This is the layout. This shows the conventional H couple, and this the CRLH based, and it shows 67% size reduction. So metamaterial has really become important for microwave, terahertz, and optical peoples. So metamaterial and metasurfaces must be a course in advanced microwave engineering at MTech. Applications of microwave engineering, very important. BTech level, they must know all the possible applications which will encourage them to study the subject, and they will understand where they will fit in future. Not only in software jobs, there are ample of software jobs. These are easy jobs, but in every batch, there are very, very serious students, those who want to take challenging jobs, and they will definitely go for microwave and terahertz and this stuff. They must know broadband microwave access for mobile communication. They will understand that the last mile or backhaul connectivity is definitely with microwave. Though here the signal processing is done by optical, but nowadays for 6G people are talking about terahertz should be used to get terabit speed. Then microwave remote sensing, then RFID, all these things are required in BTech level. In my book, I have given in the second edition all this stuff. Also MEMS. MEMS is very important. Now let me tell a few about terahertz technology. I have worked little bit on terahertz technology. I will mention that briefly here. And I have a book chapter on terahertz technology, emerging trends and application viewpoints, published by an edited book by Elsevier. So I'll say a few words about terahertz technology and applications, and ultimately I will say how it should be included in the curriculum. This is the book. Well, terahertz has the beauty that it falls in between the electronics and photonics. Thus, terahertz has both the capabilities of electronics and photonics. It has the penetration power of electronics, that is of RF and microwave, and spectroscopic capability of photonics. This has made it very, very useful. Before this century, terahertz has been used by radio astronomers to study the spectral nature of celestial bodies. But from the beginning of this century, terahertz gap has been, researchers have started exploring terahertz gap in a GP series way. Lot of research is going on terahertz these days. So our students, at least at the MTech level, should be exposed very elaborately to the terahertz. Now, question is, what are the limitations of conventional RF microwave and millimeter wave technique for terahertz signal generation? Terahertz signal generation has not yet been possible in the true sense with any electronic technique, because for GaN device, it would demand an impractically small length of the semiconductor sample. For impact, it will demand length of the transit time zone impractically small. Tube sources are limited by simple physical scaling problems, metallic losses, need for extremely high fields, as well as high current density as terahertz frequency. However, research is going on to develop innovative techniques to generate terahertz signals in semiconductor devices, either with single device, especially with impact device, or using power combining techniques. I am having a collaboration with Japan and another with USA on developing terahertz impact devices. And so what people are resorting to is the optical means of terahertz generation. There can be heterodyning of laser sources or quantum cascaded laser or irradiation of photoconductive material or electro-optic or other nonlinear crystals with femtosecond laser and so forth are more prevalent.
Professor Carr, sorry to interrupt. You have to conclude very fast because others are also there.
Yeah. So what I'm doing, I'm skipping this slides, just skipping like this, and coming to one important slide. This is concealed weapon detection. Concealed weapon detection as stand-up detection explosive is very important in terahertz technology. This shows that the terahertz has better concealed weapon detection as far as the image resolution is concerned. Then for common explosives and abusive drugs, you can use terahertz. Terahertz time domain spectroscopy is useful for early diagnosis of cancer. And terahertz communication has many possibilities for terabit communication and many other applications like whisper communication. Then apart from that, metamaterial in terahertz application is also important. Terahertz sensors are important. Metamaterial based perfect absorbers at terahertz are important. So we need to have a concise syllabus for terahertz technology and useful textbook. Tentative course structure, it is given here. I am not explaining anymore during my presentation. I have told them. Thank you all. With the words of Robert Frost, miles to go and miles to go before I sleep. Thank you all.
Thank you, Professor Kar. Yeah, Dr. Dixit.
Yeah.
Next, you can take up next one.
Sir, Professor Shivan Kaul is not available, so his talk will not be there. So may I please request you, sir, Dr. Surendra Pal, sir, to please comment on this and in general for the entire session and give some closing remarks for this first session. After that, we'll proceed to the panel discussion, sir.
Okay, thank you. First of all, I wish to thank Professor Sevgaonkar, telling what's happening in the country. There is an impression that not many things are happening in the country. But if you see Professor Sevgaonkar, there is a lot of work going on in the wide spectrum. And of course, it's in the pockets. It's not so much popular. Mostly it's the government sector and the government universities only. But there are many other institutions which are in the private sector also working for it. So Professor Sevgaonkar's inputs have been quite, nice for our paper. And what he has talked about in general thing, he has introduced in all aspects of RF technology and materials, the technology, and also applications. So next is Professor Subramaniam. Professor Subramaniam's things was to the point, and he's based on his experience and what he is doing is in his institute. I have not visited it, but I heard about from Professor Raghavan about Professor Subramaniam. What a wonderful work is being done by him, and of course I heard a lot of webinars from him. So the Professor Sevgaonkar and Professor Subramaniam's inputs will be very useful for making a paper, working paper for us. As far as Professor Chandrasekhar, Professor Chandrasekhar has been a researcher like me throughout his life, and now at the back end was his career. Now he's an academician. His inputs as a user, as an academician, has been very useful, and I think that will give us a quite insight what should be done for the country from industry point of view, from the R&D point of view, and of course academic point of view. Professor Carr went into quite a bit of details about each topic of RF, microwave, millimeter wave, terahertz, and what should be taught. And of course, his book, I happened to go through it. It's a nicely written book. And in the end, so we will take all the inputs from all the persons. But what I liked about Professor Subramaniam, the flow chart he has made it about academics, the teachers, students, industry, and user group. He has shown the interaction, and I think in our position paper that in particular thing, at least some sort of a flow chart or maybe an interaction chart will be very useful when we prepare the thing. So I thank all the speakers, all the learned speakers. They have got decades and decades of experience, and that all those things will be useful to us for making a position paper. I request if the slides can be shared with Raj Singh ji or Dr. Dixit, then that will be useful for making the position paper. Thank you very much. I wish to thank Dr. Lalit Kumar for taking the initiative. After these lectures, I find that really we are on the right path, and we should be able to come up with a curriculum. And what Professor Carr and Professor Subramaniam and Professor Shivgaonkar, they talked, we should be ready to come out with a course for MTech. BTech, we can say what are the things to be taught, but a full-fledged MTech, and the name we can decide subsequently what sort of name should be given to it, how to make it popularized. One aspect which each one of them are missing, which Professor Subramaniam, touched upon it, that from the industry or the R&D person should come on the lateral level. But to design a course, input should be taken from the various organizations in the R&D also, and also industry, what can be taught for the particular purpose. And if possible, we should interact with the R&D institutions or industries. If we train the students like this, will you give them a scholarship? Will you take them if they qualify your interviews, etc.? Will you take them? I tried this sort of thing when I was a VC with the DRDO, that if they pass for your interview, will you take it? In ISRO, IST, we have got that sort of thing. Then we train the students and ISRO takes it. And of course, some of the other organizations also take it. So that also we should make a part of our position paper. Thank you very much. I hand over to Dr. Lalit Kumar and Dr. Dixit.
Thank you. Thank you, sir, for your closing comments. Now we'll proceed to the panel discussion, and I'll request Professor Basu to chair the panel, and Professor Raghavan to co-chair the panel, and Professor KP Ray to please moderate this panel discussion. In this panel discussion, we'll have a good mix of senior academicians as well as early career academicians, as well as industry professionals, as well as BTech and a couple of BTech and MTech students, just to get their opinion on this area. So I'll request Professor Basu to please take over, and then hand it over to Professor Ray for moderating. Thanks.
Thank you, Harish Ji.
Thank you.
Yeah, isn't it? Professor
Before Professor Basu takes over as a chair and Professor Raghavan takes over as co-chair, I just have a brief point, to be made at this juncture, that panel discussions topic is RF/microwave to terahertz education for next generation, and a total number of participants besides chair and co-chair are 7, and their names are Dr. Runa Kumari, Dr. Richard Stanislas, and Mr. Vishant Gehlot. They are young faculty in the field of RF and microwave domain. Then Dr. Aviraj Jadhav, he has recently completed his PhD and working in industry. Then fifth one is Mr. Surya Teja. He's MTech students placed in Qualcomm. Ms. Akshaya, who has recently graduated in BTech and has joined in Qualcomm, and Mrs. Harshita Tolani from ISRO. So they are the participants, and since we are running late, with the permission of Dr. Kumar, maybe 40 minutes time can be cut short to 30 minutes. And
I suggest we control the time, but at the end we can expand it if the people stay back.
Okay. So now Professor Basu and Professor Raghavan can take over, and I'll be rapporteur to support them.
Okay, thank you. Professor Raghavan, please.
Yes, please, sir.
You please go ahead. Please, I'm with you. Please go ahead. Okay.
I have got, I feel very happy to be amongst all heterogeneous stalwarts. I got some few points only, so that I won't take more than 3 minutes. So that way. Okay, let me tell those points. Maybe at the end, Dr. Ray also told, or Dr. Surendra Kaur also told regarding MTech level. So let this at least start with. And power deciding people are here. I'm sure that this will be at least among the points of 16 points, 4 or 5 will definitely be taken care of. The first one is our MTech students who are getting a stipend around 15,000 rupees. Invariably, the second year project, 50% of the days, they keep spending the time in preparing for the placement training. So they don't concentrate, they don't even decide the project name. So that should be changed with, that can be done if the placement training starts from fourth semester. What I want to tell is MTech second year project should be encouraged to carry out in R&D sectors like ISRO, DRDO, NAL, etc. so that the product will be usable to the society. Number one. Number two, core engineering job should be given priority. Now everyone's dream job is to become a typist. Instead of that, core engineering job should be given priority. There are many methods for that. The third one, one or two speakers also told, computer related subjects should not be at the cost of core microwave RF subjects. Computer related subjects may be for computer science, IT. Let this be reserved only for microwave RF like that. Then we have to search where the radar, navigation, TV are for EC students. The experts who come for that, they remove it. It is not the question of the institute or the students. The experts who come for the board of studies, they have removed radar. They removed navigation, even TV. If EC students don't study TV, who will go into TV? And next one, some institutions, even this also experts have told, microwave antenna has become elective. Putting as elective, it is an indirect way of encouraging students not to catch up on. Then the millimeter subject should be an exclusive one, not microwave and millimeter. So these things can easily be done at MTech level. Then more emphasis should be on biomedical and healthcare. In the recently, the COVID time, many know how much impact the technology did with detection of COVID, and also even in therapeutics it can do. So healthcare, especially Terragants, it plays a very big role in the healthcare. I got another 5 more points. The measurement facility should be allowed for research liberally in DRDO, ISRO, etc., so that more commentable journal papers come out. If you see number of IEEE papers, China coming out more than what India is doing. China, South Korea, their papers in IEEE, because if you go to the lab, you can see the infrastructure is much more better than what is available for our MTech students in India. Then the commercial software usage at the start, instead of writing, the people directly go for, just like calculator, they go for commercial software. That should be discouraged, and they should be encouraged to write their own coding. Then they will understand the subject and they will know the reality. Then 3 more points. Instead of see, when in all the MTech courses, the BTech courses, they simply add advanced antenna, advanced image processing. Instead of repeating all those subjects, let the new topics like photonics, metamaterial, like that, let it be introduced. No adding advanced and repeating once again. Then infrastructure, lab facilities, state-of-the-art facilities are very, very less in 90% of the colleges. That's one of the reasons why good papers are not coming out. then modern should not be at the cost of conventional. Conventional is conventional, nothing can beat that. See, like IoT. Why do we need IoT? We are doing IoT without naming it as IoT. So IoT, deep learning, machine learning, those are all not required at all. We don't want virtual. We want to fight in the war scene. No virtual fighting. So no need of that kind of buzzwords. Then obsolescence removal is must. There are some equations like Dr. Subramanian told, man-hero relation. Those are all needed. We can remove it. But certain important things should not be dispensed with. Then those who are very much interested to do software, let them do on EMT. Then miracles can be done. Example, please visit Microwave 101. So our own students have done a lot, first time in the world. Then based on the standard research papers, see what DRDO, what this IPL plasma research doing, much more than a PhD. Only thing is they don't have a degree. Why can't we plan a small syllabus of based on the standard research papers, give them MS by research. Then the last one, if it happens, it will be very nice for RF microwaves. You can all think of, or you can at least recommend as BTech microwaves. Why to force somebody who is not interested in EMT to study EMT? Let them come from the beginning, like a sandwich it goes, BTech microwaves. If not at the UG level, at the MTech level, let us concentrate more on the subject alone, microwave alone. With this, I'll stop my input. I will send these 2 slides to Mr. Dr. Vishal Keshari. He will make it known to the world. Thanks a lot.
The next is Dr. Runa Kumari. Runa Kumari, sorry.
Good afternoon, sir. I am Runa Kumari from BITS Pilani Hyderabad campus. Actually, the major problem in our area is how to attract the students, because most of the students, they are going towards this placement oriented courses. So what actually we have felt when we are doing this, first of thing is this microwave, we have only one core course, which is microwave. And that is not only in our institute, in most of the institute, if you will see, I have already seen some comments from the our participants. They are also mentioning that in most of the institute, only one core course is there in our area, means RF and microwave. Rest of the courses are elective courses. So elective courses, when we are doing the survey of elective courses, out of 100% student, only 10% students are interested for RF microwave elective courses. And what we found that nowadays most of the students are placement, they are finding out the subject which will help them during the placements. So the number of actually jobs, if you will see in core companies, it is very, very less. So first of the thing that we have to find out some more jobs in our area. Then second thing that actually to attract that student, because students are now, they are interested for hands-on with these theoretical things, they want hands-on. And few of the institute, if you will see that it is not possible for them to buy this software which is related to our area, RF and microwave, which is very costly. So if we can do something to get that, means this whatever software we are using in our area, if it will be available to the student, open source software, then at least they will maybe attracted towards this course. And one more thing that we can see that this for measurement purpose, if we will see, we are having so many instruments which is very costly. If we can explore some instrument which is actually cheaper in compared to, like for example, if we see VNA, only up to 12 or 13 gigahertz VNA, if we'll see, that is also very costly. Like we have to pay 8 to 10 lakhs or 2 lakhs, which is not possible for most of the institute, like private institute. So in our area, if we are only studying the course without any hands-on, it is no use. They can visualize the subjects if we will have some hands-on on that. And for that, we have to do something so that they can get the simulation software facilities, the measurement facilities. Then only maybe we can attract more students. That is actually my observation.
Okay, thank you, madam. I mean, I request speakers to introduce themselves, I mean, telling their institute's name before they make a point. So next one is Dr. Richard Stanislas.
Okay. Thank you so much. So I had actually prepared a set of slides which I'll be sharing it with you. So I'm Dr. Richards from assistant professor in School of Electronics Engineering in VIT Chennai campus. So as ma'am also said, so and all the speakers have said, the job opportunities actually which we need to assure in the fields of wireless communication, MEMS, microwave engineering, radar RCS design, and ATR and stealth technology, antenna analysis design, EMI, EMC analysis, remote sensing and non-destructive evaluation, biomedical engineering, so physics-based signal processing, computer chip design, laser and optoelectronics. So in all these areas, we have scope for electromagnetics. So that assurance should be, the job availability should also be made available. And regarding attracting young students and faculties to the area of RF microwave engineering, so many medium and small scale industries are nowadays involved in supporting DRDO projects through Make in India initiative. So faculties and scientists may visit industry conclaves, defense expos, where we can interact with the industries for their requirement. And industry-sponsored consultancy projects may also be taken wherein we can involve the students and faculties for product development as well. And regarding developing courses on microwave to terahertz way for UG students to be relevant to the needs of industry, so we can take additional courses on computational electromagnetics. We can involve technologies related to 5G and 6G, and again EMI and EMC for beyond 6 gigahertz. It is still under standardization process, so we can also cumulatively start working on that aspect as well. And industry collaboration is the need of our for developing courses that can cater their needs as well. And we as an academic and research community as well, we'll also get exposure to the various standard designs and manufacturing processes. And regarding improvements in accessibility of technical laboratories and research facilities, so there may be a single repository of resource laboratories, I mean, wherein multiple resource centers are there. So those details may be put up at a central repository wherein people can access and look at the nearest facility available for EMI, EMC test facility, be it antenna and RF characterization, fabrication facilities, hyper microwave testing facilities. So in this way, both academic and industry institutions will be greatly benefited. And regarding the national initiative on the development of open source EM software for simulation studies. So as ma'am also said, the commercial EM softwares are really expensive with respect to academic institutions, because even the academic research licenses are at, which are provided at the discounted pricing is also quite high. And the industries, obviously, I mean, the industry license is further much costlier, and small scale and medium scale industries cannot afford investing in purchasing the software license as well. So academia, in collaboration with national institutions such as DRDO, CSIR, ISRO, SAMEET, etc., should come up in developing open source EM software solutions, wherein we can also support the industries and the academia as well. So regarding the global trends, the last point on which was stressed upon this presentation. So global trends and futuristic topics in RF and microwave and millimeter wave and terahertz area. So again, a repository on ongoing funded projects and the corresponding industry and academia participation within our country. So if that is made available, then again, people will get more exposed to it. And research problems on national interest may also be regularly updated in such repositories wherein we can again look upon it and write more funded projects and involve much students, so that the interest will obviously will be inculcated looking at the research output as well. And the webinars on awareness related programs to global trends through invited lectures from international programs may also be involved, as it is already ongoing in the vacuum electron devices group as well. So having said this, again, we also, from VIT Chennai, actually, we have an anechoic chamber facility which we offer consultancy services, as in the antenna characterization for industry and academia as well. Up to 18 gigahertz, we have that facility. So that I just wanted to mention if anyone is interested in the nearby region who want to come over here and present it as well. So yeah, this set of slides, I'll be sharing it with the host. And thank you very much for giving a wonderful opportunity. I thank the INA group, CSCR, Siri Pilani, Bits Pilani, Hyderabad, and VED Thinkers group as well for giving me an opportunity. Yeah, thank you.
Thank you, Dr. Richards. I mean, all these points are noted down, and then maybe when we sum up all the points, we would like to touch upon various points and try to discuss.
Sir, can you hear me? Can you hear me?
Yes.
I have to say something. See, I request both Runa and Richard to make an abstract of their suggestions and talk, and send it to you. Both and other participants may make a and then send it to you, isn't it? That would be very nice for making the paper.
Yes,
sure.
So that is my suggestion.
Right, sir. The next participant is Dr. Vishant Gehlot.
Very good afternoon to one and all. Myself, Vishant Gehlot from Banastari University. We are here starting the microwave education as well as the research when I joined here in 2014 after completing my PhD from CSR Siri Pilani. So here we have given us, you can say, main course in a master degree for MSc in physics, and we have certainly feeling the same number of challenges which has been discussed by all the speakers and especially by the Ruma ma'am, how to attract the students for this particular stream for microwave and all. But as far as the time period I have been during this professional teaching education, so I have been feel that there is some lackings in the curriculum, as we have these been implemented to the you can say the knowledge implementation by the graduate or postgraduate student for the further experience of research, as well as they need to be a structured continuation learning environment. And the main thing is that the retainability of micro students due to the you can say low job attraction in this particular field. These are the main things. As far as the things to be challenges, we have converted the things to buy some you can say, as the Richards and Ruma ma'am said, that there is a heavy commercial software which has been costly for that, but some of the agencies are there who provide the student version. We have been added on that could be a part of suggestion, so that student can learn about the CST student version, and many more are there available for the less cost cutting prices. And these things to be converted for the part of once, say I have an example that two of my PhD student has completed their PhDs in the field of topic of gyrotron and as well as the TLOT. But after they complete, they are not continuing their research in the part of research in the microfield and devices. So that is the lacking, so that we can retain the students and the coming products, so that they will continue the part of next level for the research. That is the main problem I'm facing for that. And the addition of some kind of problems we can doing that, we can have a collaboration inter-university, like we have a VNA and we have a facilities for you can say antenna measurement up to the 26 gigahertz dynamic chambers and VNA up to 40 gigahertz. And also we have making some collaboration, like we have collaboration with CSR, CDP and other universities where the large facilities are available. So we can be continued and make it progress for the one and all times. Here we have started with, as Brian Basu sir said, research is starting in second, you can say, PhD for India IoT, inductive output tube, for the, you can say, point of sort of collaboration between multidisciplinary projects. And we have just started to make the things attractive by the application point of view, like terahertz application for agriculture, where we have started seed germination using terahertz radiations. So these kind of things we could be attractive, but again, we have limitations to be kind of things to support as a kind of funding and all. I have been applied for the, you can say, ISRO's response scheme for a project, but we have lacking of fabrication and faced the rejection of that project. So again, fabrication part of that will be a great challenge for the prototype, or you can say go for the advanced research, so that we can convert the student attraction with the particular field of microwave and RF to the radiation RF terahertz spectrums. So that is all I just wanted to say and add on my views. Thank you so much for giving an opportunity to discuss my views and experience with this. Thank you, one and all.
Dr. Gehlot, as the chairman has suggested, you jot down these points and then send these things to.
Sure, definitely I will do so.
Yeah. Any point you would like to make, sir, chairman or co-chairman?
Okay, I think he had expressed some point of his concern. I think Professor Surinder Pal, Dr. Surinder Pal, he must be listening to it. I don't know. So he will please take care of his problems and make a solution to this problem. Dr. Pal, if he's there, he'll take a note of. Next speaker you can go to. Yes.
Yeah. Next speaker is Dr. Aviraj Jadhav. So he has done his PhD from IIT Bombay and is working in industry. So he has got the mixed or best experience, so he can share with us.
Hello, can you hear me?
Yes.
Yeah, hello, sir. Am I audible?
Yeah.
Yeah. Okay. Yeah. Thank you, KP Desa, and thank you for this opportunity. I'm very honored to be present between my mentors and my ideals today. So the starting off, like what I feel is that the students, the biggest motivation is what would be the next after their degree. The biggest motivation is what job they will get. And that question is like a common thread between all talks and everyone's mind. So the scenario in the industries was like that government jobs were only there in RF microwave, which was the scenario like 5 years ago or like decades ago. But currently, I'll say this scenario is changing, and the things are improving in industrial sector, especially with government policies changing, like IDEX challenges and all. So I have recently completed my PhD and I have joined a company called Precision Power Products, which is a company, an old company, but they are just now starting in some RF microwave cavity activities for defense related technologies. And such applications are which I am seeing in this industry are completely different, which I have never seen during my coursework in my even in B, MTech or PhD. So the thing is that students and teachers should be aware of such opportunities, such applications, like what Professor Shivgavkar also touched upon, that some astronomy is there, nuclear fusion related. Even Professor Dr. Richards also mentioned many of the applications in which electromagnetics, RF, microwave, terahertz. It's such a vast field, and it has such so many applications and so many industries, not only in India, even internationally, are working on. So there are lots of opportunities, but we should identify what skill set is in demand by these industries. And one major factor is that the industries does not look for just device. They look for product-based thing, system level thing. So the students have to be taught how this small theories, small devices can be consolidated or used in a system and can be translated in a system, which Professor Subramaniam and also Professor Subal Kar had mentioned about teaching them some simulation designs, simulation software, and translating, suppose there's the oscillator design or the amplifier design or the power amplifier design, and taking it to the level where the fabricator can fabricate. Even if you do not have the fabrication facility, you teach it to that level that the fabricator can take it up and it can be practically implemented. And such skills will be appreciated by industry people. And now the current situation is that the industries are in India, at least, are in a very nascent stage, and we do not have the liberty of recruiting like army of people for these jobs. So lots of responsibilities are on the individuals, and that individual should know lots of things in this field. So to train them is not an option for the industries. They have to be taught by the academics only, and that's why we have to carefully plan the curriculum from second semester itself. We have like 6 semesters. In addition to that, if we can have workshops, rigorous hands-on workshops to teach the students some hands-on things like oscilloscope, use of VNAs, and all these practical aspects. So that would be very beneficial. And we have to look up to the requirements of international companies also, so that students are motivated to in this area. And we have to work not to just prepare workers, but we have to work to prepare leaders in this industry. And
Yes, Dr. Raviraj, any other point?
yeah, I can take any questions or any suggestions from anyone.
Okay, so as mentioned by chairman, you also write down all the points and then send whatever you have, views you have expressed.
Yes, sir, definitely. Thank you.
Thank you. The next speaker is Dr. Surya Teja. He has recently completed MTech.
Pardon, I'm not doctor, sir. So I'm just a student who completed my master's now. Okay. First of all, good evening to everyone. I'm a very little person to speak in front of you all. There's so many eminent personalities here, like that the person who learned subject from them, they are giving, I am in a live presentation with them, which will be immense opportunity to share my feelings. So instead of writing all the points, I will support the points which are mentioned by different members. First thing is, BN Basoi, the sir mentioned about changing names of the subjects or changing names of the course that you introducing. It may be appearing as a small point, but it will affect a great impact, because small changes will make a great impact. So instead of, suppose recently, I went into a bookshop where they're teaching 5G. So for teach 5G, they have to know 4G. The speaker mentioned first to learn 5G. First, you have to learn 4G. Then the audience are like, we are come for 5G. First, teach us 5G. So this is the type of mentality the students will have. So if you are, if only the courses are with the same traditional names, they may be like, okay, this is a traditional course. Then there will be the same mathematics thing, same all these things, the mathematical journal, which we can't even crack it. Then this time of dilemma will be in the minds of students. And second thing is in the job opportunities. Really, I'm from undergraduation where I don't have any resources to have this microwave, including the microwave test bench setup. So I don't know whatever the things I know about microwave is just mathematics. But after when I come to my MTech level, there I have exposure to all these things, softwares, all these things like microwave test bench setup. Then have interaction with the PhD faculty members who are working in current industry projects. Then indirectly, who doesn't have interest on all these RF microwave things, gradually develop interest onto these things. So the faculty interaction and the PhD members who are pursuing in that field have interaction, and real-time projects will play a key important role. Another thing is job opportunities. So most of 90% of the MTech students will be in a mindset that I have to get a job. So they'll go search for a better job. Suppose if one company is giving some 1 lakh salary, so even though I have interest in RF domain, working for two or 5 or 6 couple of years, even though my salary is not that much, I mean, he'll be in a mindset that why I'm working all these years for my passion with low salary. So this is the type of difficulties that we are facing as masters and BTech also. That's it, sir. That's my point.
Okay.
Sir, I got one point with respect to Dr. Aviraj and Mr. Surya. Both told when they went to the industry, they don't see what they have studied in UG, PG, or PhD. It is 100% correct. Many of the places, what they study, they don't see in the industry. But I know there are some institutes where they teach what they practice, and what they practice they teach. For example, one subject like micro-integrated circuits, fully designed, and the same thing they do it in the laboratory. So definitely when such people go to DRDO or NAL and question the comment like Mr. Dr. Abhiraj will not come. What they study, what they design. In fact, Dr. Subalkar has elaborately told in that book, it cannot be taught in a single semester. So one can think of MTech on this line. In any case, people should not simply teach theory alone. Both should marry. Teach what you practice what you teach. This is very much being done. I do not know about other institute. Definitely it is done in IIT Delhi, especially in RF microwaves MTech. Thanks a lot.
Yeah, yes, sir. So that application-oriented teaching, so that they have practical knowledge and that is required by industry is very much essential. So Mr. Surya also is requested to write down the points and send to us. Okay, the next speaker is Miss Akshaya, who is again placed in Qualcomm. So her view.
Good afternoon, everyone. I'm Akshaya, a 2022 bachelor's graduate in ECE from BITS Pilani, and I'm currently working at Qualcomm. I'm here to share my opinions on what additions might make RF microwave engineering education better. Firstly, I feel that there should be more exposure through projects. Actual design projects are very different from textbook ones. So when students are part of such projects, they can understand demands and constraints in real world problems such as size, efficiency, bandwidth, power, cost, availability of materials, etc. Textbook problems are predominantly formula based and take minutes to arrive to a solution on paper, but they only result in a first cut design, which requires a lot of further tuning and many iterations to produce the final design. And this process can actually take up to multiple months. So this kind of exposure will help students really understand the process. The second thing is that there needs to be more focus on the overall system level design and apart from individual subsystem design. For example, there are many modules on a mobile platform card, and RF card is one of those modules, and all of these modules will affect each other. So this will help students get a bigger picture and appreciate the entire problem much better. Thirdly, I feel that there needs to be education on different standards in communication. Companies deal with these kind of specifications, and it would be good for students to have an idea of the kind of frequency, bandwidth, data rate, power, and architecture of such standards. Fourth, I think that there can be coverage of design of circuits like power amplifiers, low noise amplifiers, etc. Because they are important components of RF front end, which are very important to preserve the signal integrity of whatever is incoming to the antennas. So I feel that the inclusion of the above points would make RF microwave education even better. And I thank you for the opportunity given to me.
Okay, thank you, Akshaya. You made very pointed observations, so you also kindly write down all the points and send to us. And last speaker is Miss Harshita Tolani. She works for ISRO, I'm told. So her views.
Yeah, good evening, everyone. I'm Harshita Tulani. I'm working in ISRO currently for bridging the technology gap between the microwave end of the spectrum and the infrared on the other side. So what I feel is the major thing which is missing is the experimentation part from the curriculum. So I am myself MTech from IIT Kharagpur. So what I feel is theoretical part is okay. It's covered very in like quite in depth with the almost all the spectrum is covered, but the experimentation and the tutorials are missing when it comes to the curriculum. So hands-on tutorials, they have to go hand in hand with the theoretical class for better understanding. It should be supported by projects for experimentation so that the students can correlate from the analytical point of view to the simulations, to the actual fabrication and the measurements. So this is about the portion which I feel is missing. Now, coming on to the subjects which should be covered is it requires actually a multidisciplinary field. So devices and the solid state device physics is the most important part, but then that is just the base to start with the development. So it has to be followed by the circuit designs like everybody mentioned about LNAs, oscillators, passive circuits, then the subsystems where these circuits are employed like the transmitters, receivers, the transmit receive modules, followed by the systems, the radars or the radiometers where the subsystems are integrated, and the end application for which all this development is happening. So the complete chain has to be, brought into the picture, into the study for students to better appreciate and understand. Now, coming on to one of the points made by one of the participants or the panelists was that the respond projects are not supported when the fabrication facility is not available. I am myself mentoring many respond STIC projects where we do support fabrication, and also now we are trying to bringing in startups for supporting the fabrication part. So that can be handled. So what I feel is more and more students should be brought into the respond projects or into the industries for their master's projects. So all these things will make them give a complete picture and make them more will develop their interest into this field, which at present is missing to some extent due to their less exposure to the experimentation part. So this is my opinion.
Okay, so thank you, madam, for your views. Kindly write down all the points and then send to us. There are very good points raised in the chat box. So before we go to them, I'm also told that Professor KP Maheshwari is there in the audience. So he has also joined. So we request him to express his views. He's a very senior professor, and then he has worked in this field. So his views are very important to us.
I would like to add something.
Yes, sir. Yes.
Professor Maheshwari has the credit of developing the first ever relativistic backward wave oscillator in the country. He and Professor Chwell, his student. So Professor Maheshwari is so nice that he has come. And similarly, Dr. Raju is there, a very senior scientist of CD Pilani, ex-scientist. He will also say a few words. Please, Professor Maheshwari. Professor Maheshwari, yes. Professor Maheshwari. And then Dr. Raju will also say a few words.
Hello.
Yeah. Yes. Yes, Professor.
Yes, I am KP Maheshwari.
Yes.
Actually, the microwave component is very much in MSc Physics 2. And their theory is taught in a very deep way. But however, the experimentation is missing. This is the drawback. Otherwise, this is done at a very deeper level and a very thorough level, especially at the level of J.D. Jackson. So my submission is somehow the MSc Physics is a partial component of microwave engineering. And this is compulsory. Electromagnetic theory is taught in a very elaborate way and asked in the examination, and it's compulsory two semesters courses.
Exactly.
So, but the experimentation is missing because of money and also lack of expertise in this field.
Okay.
Yeah.
Thank you. Thank you, Professor Maheshwari. Professor Ray, KP Ray. Professor Ray.
Yes. Yeah, Dr. Raju also, if he is there.
Yes. Dr. R.S. Raju, please. He has the world record of developing high emission cathode. Yes. Dr. R.S. Raju. Dr. Raju is there? Hello, Dr. Raju. Dr. Raju. Hello.
He is not there. He's not there.
If Dr. Raju is not there, I invite Professor Jamil Akhtar. He's a very fine researcher and very good teacher. So his views we would like to hear. Professor Jamil Akhtar.
Sir, Professor Akhtar had a class. He had to leave. I am not sure whether he has joined back.
Okay. Then we would like to go to the chat box where the very important views are expressed by various researchers, like Mumtaz Ali has expressed his views, saying that he is very much impressed by what is presented by Professor Shivgaonkar, but he also has shown his apprehension about the job opportunity. These courses, they don't lead to good job, and only limited to government job. So that is his views. And then he also has said in another message in the chat box that that experimental that facilities are limited, so if those facilities are made available, it will encourage students to go for this field. And two more points are expressed by Dr. Saroj K. Patro. She expressed her views that combination of what Dr. Chandrasekhar and Dr. Shivgaonkar has said, those things, if combined, will complete the whole gamut of the topic. So she has also written that government jobs are very few, and then that private organization jobs are not there for this RF and microwave. That we will address too at the end when we sum up, because now under Make in India program, lots of job opportunities are there in private sector as well. So these are some of the important points raised in the chat box, and they, most of them are similar to what that that speakers in this session have emphasized, that measurement facility, lack of measurement facility, that teaching which is required by industry. So all those points which are spoken about by these 9 speakers are also reflected in the chat box. So now we will come to the summing of this session. So
Professor Ray, I'll just interrupt you.
Yeah.
Professor Jamil Akhtar is there. You have to unmute him and invite him.
Okay, I have unmuted, sir.
Harish, you can unmute him, please.
Yes.
Is there?
Now I can. Yes, please.
Yeah.
So, Dr. Ray, should I?
Yes, please.
Okay. So, thank you for inviting me. And I joined this webinar little late, but really it was very interesting, of course. As far as the concern of the academic scenario under this domain of microwave to terahertz. Certainly, this is very emerging area. And I have seen recently in Manipal University, Jaipur, where I spent 3 years. Of course, I agree with the statement given by Professor Raghavan Saab that the core engineering actually areas, they are not actually being taken care of as the challenge actually has been given by the IT. Now, I have tried there also to establish some kind of activities related to high frequency device characterization and so on. But actually a little encouragement actually was observed, of course. So I don't think that this cannot be taken up because it is up to the faculty and the people actually who are engaged in our academic institutions that how they actually provide this area before the students. As in Siri, we were fabricating the impacts in late 80s for DRDO, and we developed the impact down at 94 gigahertz, and the technology was actually very interesting. So when I see and back that nobody actually working on these technologies, on the characterization setup and other things. So I feel that it is up to the experts actually who are involved in the institutions. They should try their best so that actually people, they know about the design and the attraction actually behind it. Everybody talks about the 4G and 5G and now 6G. So this is the area actually we should try to introduce and try to contribute. And in my opinion, actually this is the very right time that we are talking about these things. And I'm very sure that certainly it will be a very attractive area very soon. So I'm very hopeful, and I'm also trying to do here also. And so I'm very happy to be here, and I have listened very good actually talk from the professor from Calcutta University, and he talked about the impact and other things. So thank you very much, especially Dr. Lalit Kumarji and the team and the seniors working in this area. And whenever actually anything is required from my side, I'm always available, and I will be very happy to contribute because transit time device technology is actually rarely people are talking nowadays anywhere. So I remember the Delhi University group, they were the pioneer in the beginning working on the microwaves. And Dr. Amarjit Singh, actually, he was deputed in Siri Pilani because he was there in the microwave area and he was associated. And that's why the Siri Pilani has the microwave tubes area, and this activity started. So such kind of actually thing is very much required now, considering the practical usage in communications. And perhaps this combination of optical and optical communication will be also a part of this. So as micro machining was also discussed somewhere, so MATS technology has given a further actually stage where we can introduce this technology for terahertz devices. And experts are there. Perhaps we can actually formulate such kind of courses in our academic institutions where working prototypes are there. And of course, antenna is there. Antenna technology is going on to be changed a lot, keeping the requirements. So with these words, sorry if I have taken the long time. Thank you very much and happy to meet you all.
Thank you. B.N. Vasu speaking. Thank you very much.
Please.
I'm B.N. Vasu speaking. Dr. Akhtar, thank you very much.
Please. Thank you, sir. Thank you.
Thank you very much. Yes.
Yeah, thank you, Professor Akhtar. Any other participants from the audience would like to make any point?
Dr. Raju was trying to contact. I don't know, is he around or not? Dr. Raju? No? Okay. Okay. Dr. Raju? No, he could not enter probably. He could not join somehow, some technical problem. Technical problem. Okay. Okay. Please go ahead, Professor Ray.
Yeah, so before chairman and co-chairman will start summarizing about the session, if any other participants would like to, make any point.
Dr. Ray, I have got one point to make. I'm KP Maheshwari. One.
Yes, sir. Go ahead.
We have discussed conventional microwave electronics here very much, and very good suggestions were obtained. But however, a new emerging field, relativistic microwave electronics, is coming into picture. This is, if not a part of a curriculum at BE level or ME level, but it is a very important part at a research level. This should be somehow be included, because this modern time is for high energy microwave field. That's another new part. Low energy microwave is being done here very much, but when energy is very high, and relativistic microwave electronics is a new field, it should be done. At least it should also be encouraged. I mean,
yes. It is of tremendous defense interest also.
Yeah,
defense
yes, sir.
Tremendous.
Yeah,
And
yes, sir.
May I just comment a little?
Yes, yes.
Professor Maheshwari has raised a very important point, and Professor KP Ray can, I think, elaborate on it. The high power microwave course that they are running at MTech program in DIIT.
Yeah,
We are able
we
to
have
introduce gyrotron, like Professor Subalkar's book contains gyrotron. You are basically a little bit touching the relativistic electronics. So, KP Ray, I think you would like to comment something.
Yeah. I wanted to tell that this course is being offered in DIIT since last 5 years, and we take help. Most of the portion are covered by Professor Lalit Kumar himself. So those things are done at DIIT, sir. And then I was told that even IIT Kharagpur was planning to initiate one subject in MTech course on HPM.
Yeah. Right.
Okay. So now, Professor Basu and Professor Raghavan, can summarize the session, and then at the end, I will put forward my views.
Before Chairman Dr. B.N. Basu summarizes, I just want to tell only one point. It's really a very sorry state of affairs. The last speaker of this panel session, she told she studied a very deep theoretical point on microwaves, but the laboratory facility is lacking. So that shows her high standard. If a Kharagpur IIT is known for microwave and radar, one building is for radar, one building is for source. So if she has told such a remark, definitely everyone can think the level of other institution in India. So what I want to tell is, people expect very high standard, including the speaker from the Kharagpur IIT. This is a good initiation done by Dr. Lalit Kumar, Dr. Basu, Dr. Raj Singh, and going to be put in a nutshell by Dr. Kesari. I am sure with people like KP Ray, Dr. Surendra Prasad, as you people going to attend all BOS, you should definitely see that this 3 hours session brings a sea change in the microwave education in India. So that way I find this 3 hours session is going to be a key opener for RF and microwave. People don't come here, but they don't throw their cell phone out. They want to make use of every facility of microwaves, but they don't want to spell the microwaves. So now I am sure that rule makers here, starting from Dr. B.N. Basu, will bring a big change. And no more Kharagpur student will say there is no laboratory facility. If Kharagpur student is telling there is no laboratory facility, everyone can understand what is the level of other facilities in other level. People say NIT Trichy stands first, but I know we used to beg some other place just to get the measurement done. So I hope all the things will be solved by this session. Now I give this to Dr. B.N. Vasu.
Okay, thank you, Dr. Singravellu Raghavan.
Thank you, sir.
Now, I did not, I was surprised how I think she is Harshita Talani.
Yes,
Dr.
sir.
You are in IIT Kharagpur.
Sir,
Okay.
actually, I'm in ISRO right now, but I did my master's from IIT Kharagpur, and my master project I did from Technical University Munich, Germany.
Okay.
Through that
Munich.
scholarship, sir. Yeah. So actually, I mean, sir, after going to Germany for my practical project work and studying in IIT Kharagpur for the first year where the coursework is done, I actually had best of both the worlds because I got the best theoretical background from here, whereas the advanced experimentation portion at Munich. So after coming back, I strongly felt in India, if we can improve upon the experimentation part, then definitely, I mean, it will work wonders. So that is why
Okay.
I made that point, sir.
I would like to share with you my experience with IIT Kharagpur before you were born. It was in 1968. I was in that microwave lab you are talking about, and I was doing my doctoral work with Professor Chakravarti. There I have noted, say, for instance, Harimohan Gupta was doing MTech. Harimohan Gupta of IIT Delhi. So you can ask him also. All facilities were open to MTech students. Whatever there, you know, that was the lab set up by Professor G.S. Sannal, Professor B.N. Das, all stalwarts. So I'm surprised how this change has come. I had never visited Kharagpur recently, I don't know. But that year, I mean, that time, I'm talking about 1968, 67, I was there. So there, I am surprised how you are saying that their facilities are not good and open to microwave. Anyway, this has to be looked into.
Sir, I did not mention that it is not good and open. I felt that the experimentation part is missing in the curriculum.
We'll look into it. Thank you. So you write these things and we'll make a
Sure,
note of
sir.
it.
Sure, sir. So probably because I did my master's after working in ISRO for 2.5 years, so where I had exposure to the experimentation as well. So probably that was the reason I thought that the experimentation part can improve over there. Otherwise, sir, I have no complaints about doing my master's from IIT Kharagpur. I'm proud of it.
Thank you. Now, I am coming back to Professor Ray. Professor Ray, it would be very nice, say, instead of my summarizing everything, all inputs go to you, and then you make a summary and make it available to Dr. Lalit Kumar. It would be very nice, and maybe we can all together edit the fallout of this validated, what is that called? This panel discussion. Okay, so that will be a good thing. So instead of my summarizing, and then it will be made available to the organizer, Dr. Lalit Kumar, and Dr. Surendra Pal and others of INAE. They will do it. Okay, and Professor Raghavan, if you have anything to say, you can add. And let us close it, close the session. See, I from 2 o'clock I have been here. I have not left the meeting any time. Okay, thank you very much. Thank you.
Sir, with your permission, I would like to make a couple of points here. I mean, which have been raised by all the speakers and also some of the chat book points I wanted to address. First thing is about the measurement facility. You know, I mean, the lack of measurement facility was emphasized by many speakers. Sir, as a researcher, I mean, I feel that if someone tries to measure some characteristic of some developed components, all the advanced lab, like in IIT Delhi, in DIIT, IIT Bombay, or other ISRO and DRDO lab, they encourage the use of these sophisticated equipments. If someone has designed and developed some components, and then at very nominal cost or with no cost, they are allowed to do testing. So that if someone is really keen to test these things, they should approach these labs, and then these things are encouraged now. So that is one point. Second point, which was told, that in devising the syllabus, industry requirement has to be incorporated. I have been in board of studies member of a couple of IIT, and then also we conduct in the IIT. All that board of study committee, there is industry representative, so that what is required by industry is generally taken into consideration, so that the courses are not open-ended. So, and also third point which was raised was that there should be that is invited speaker from industry and various labs, so that students get exposure of, they hear from horse's mouth, in a that straightforward language. That is facilitated in most of the places. Like in IIT, we always encourage. I have experience of IIT Bombay. There also these experts are called as a part of the course. So that is always done. Maybe like that should be. That message should be spread, that even private engineering colleges should also have those type of arrangement in board of studies. And final point, which is about the job opportunity. Recently I was there in Solapur for commissioning of the radar, which is developed by private industry in India, and that is working on 24/7 basis, used by Ministry of Earth Science. And in Solapur and Tuljapur, these two radars are working. So what I find now, and also that has been the policy now, that this most of the repetitive work, or to some extent even development work, industry is assigned. They are doing that, and under this Make in India program, lots of thrust is given, so that industry get integrated with various ISRO and DRDO lab. And one of the industry person, I will not name, who was present there, was telling that it is becoming very difficult to get that automated vehicle, and then automated radar, automated driving, with that type of requirement coming from the industry. They are telling that they are finding it very difficult to retain good people.
Yeah.
And he was telling that most of the DIIT trained students who join there as scientist or engineer, they get 3 times jump or 4 times jump, and they are absorbed. So they are telling that there is scarcity of these trained people in this field. That is the recent feedback I have got. And then all the time we keep getting requirement from data pattern, Astra Microwave, and then all other industries. So my view here is that things are changing now, and with the emphasis of Make in India program, and then a strict implementation of Make in India program, and Make in India campaign, I think in this field job opportunity will increase manifold. So these are some of the points I thought I'd share with you.
Yeah. So you also record your points and make it a very good outcome, fallout of this session. Thank you.
Thank you, sir. Yeah. We hand over the floor to Professor Lalit Kumar then, and Professor Dixit.
Yeah. Lalit sir, would you like to make some comments, or should we go ahead with the plan?
Yes, sure. So I think we stretched the time quite a lot. We are at about 6 o'clock now, about an hour. So I would like to say that I had a wonderful session beyond my expectation. And I must thank the session chairs, Professor Surendra Pal, for the first session on invited talks, and Professor B.N. Basu, Professor Raghavan, for the second session, Professor Ray, for the panel discussion, which has been very interesting and very thought-provoking. I would also be wanting to thank on my part Professor Shivgaonkar, Professor Subramanian, Dr. Chandrasekhar and Professor Suvalkar for very, very informative and very pointed and useful talk from the point of view of all of us and particularly the expert group. I think the points which have been made are very, very pertinent by all the people. I also saw the participants' comments. So what we see is that definitely we all feel that there is a need for bringing a change in the content and the style of teaching this subject at graduate and postgraduate level. That all of us seem to agree. And we have to work out on how it is to be done. People have also pointed out that there are no good teachers at many places, there are no good facilities in many places, and no good softwares available other than the imported ones. So this is another issue I think all of us will try to address, and I invite comments. Problem is there, but what is the solution? Much of the solution lies also possibly in self-help. For example, the open software can be done by consortium approach among the academia and the R&D institutions and industry. And similar way, a simple network analyzer or measurement instruments. I think if I go to any teaching micro lab, they only have that Clastone as a source and expert waveguide components, nothing beyond that. So this is something we can, as a nation, which is so much manpower and so much technology, we can rig up a small, simple network analyzer, a scale network analyzer, antenna measurement facilities already being done indigenously, and other such experiments in metamaterials and so on. So I think the consortium approach would be something which we should work on for software and for basic instrument development for teaching. That's what I think. The other thing is, as Professor Reyes pointed out, is the scenario of employment is changing. Government would hardly want many micro engineers, but private industries are definitely going to demand small and MSMEs who are catering to DRDO, ISRO, and to these communication giants, basically. Those are going to need a lot of micro engineers. Other killing application, for example, I would like to mention one example of the diamond industry in Surat, lab-grown diamond industry. I'm told, I'm sitting here in Siri by the Siri colleagues as well as others, that in Surat itself, they want to set up 10,000 plasma enhanced CVD machines, each one needing a 6 kilowatt magnetron, and this magnetron will run only for a few months. So they will be having multiple thousands of requirements of 6 kilowatt magnetrons only. It's not magnetron, they are going to rig up the entire system here. So all the plumbing components and everything which goes into a RF transmitter will be rigged up in India. And this is being done, mind you, by mechanical engineers. Micro heating systems, many people are doing. Mechanical engineers or electrical engineers, nobody is there in microwave which is working on that. So the technology has come to such grassroots level. So I think there is definitely a need for us to wake up and put our efforts together to try to make a dent in the Make in India and the Atmanirbhar Bharat in this technology. And we have the capability, and we only have to have collaboration and will to do something meaningful. We all, I think, have spoken the same language which I just summarized. So I think I request all of you that this webinar is not the end of the story, it's the beginning of the story among all of you. And I request all of you to please remain connected. Your, I think, email addresses are already there with us. Remain connected and contribute to our development of the work that we want to do for the position paper and beyond, to find solutions, real solutions. There is also a need for teaching the teachers. So this is another thing, because if you have to teach new subjects in a new way, then the need of teaching teachers and developing online courses, virtual laboratories, and so on. So all that work is also something which all of us have to do collectively. So at the end, I would only thank all the organizers from my side who have done tremendous work to put it together, all the attendees who have stayed till late and have participated with full josh. Thank you very much. And I look forward to your continued association and cooperation. If I missed anybody, please forgive me.
Thank you, sir. Thank you.
Thank you, sir. So I think we can close this webinar, sir, with your this, or should we have a formal vote of thanks with this?
I think let him make, because very brief, I think, just 2 minutes.
Okay.
Just
So
take 2 minutes.
okay. I'd like to invite Dr. Ayar to give the vote of thanks, formal vote of thanks for this webinar.
Hello. Am I audible?
Yes.
So first of all, on behalf of the INE expert group, I would like to thank Professor Surendra Pal and Dr. Lalit Kumar for presiding over the webinar. It was a wonderful webinar, as we see. And also, I would like to thank Dr. P.C. Pancharia, the Director CSIR CD, for supporting the INE expert group. And my sincere thanks to the eminent speakers, Professor Shivgaonkar, Professor Chandrasekhar, Professor Subramanian, Professor Suvalkar, for spending their valuable times and shared their views with their wonderful talks. So we have learned many things, and I think that would help us to make that position paper. I also express my thanks to the panel chair, Professor B.N. Basu, co-chair Professor Raghavan, and moderator Professor K.P. Ray, and all the panelists for a very fruitful discussions. I think many important points has came out through the discussions, and that will definitely help us for the determining a curriculum. And I thank Professor K.P. Ray, Professor Harish Dixit, Dr. Raj Singh, and Professor Jalil Akhtar for smooth conduction of the entire webinar. And on the organizing front, I thank BITS Hyderabad, led by Professor Harish and his wonderful team, who has done a very wonderful job for arranging all these things, all these the web platform and all these things. And then the VED Thinkers group, led by Professor B.N. Basu, and aided by Dr. Raj Singh sir and Vishal Kesiji. So thanks, sir, for your support for this webinar. And all the INE expert group members, headed by Dr. Lalit Kumar. And at least but not last, I would thank all the participants who has participated till late with full enthusiasm to make the webinar a success. And also my team here, the CD team, who has participated in a big way. And I also request all the participants to kindly give their feedback if there are something left through email, so that nothing is left out and all things can be included in the proceedings. So that is all from my side. So thank you all.
Okay, thank you. Okay, thanks for the best contribution and all. Why, Professor Basu, we only see your hand. We're not able to see your face in the entire webinar. Professor Basu, we are not able to see your face.
Okay, my laptop was not working.
Yeah. Yeah, I know.
Okay. Take care. Okay.
Night and a good night.
Thank you, Dr. Professor Dixit. Thank you.
Okay. Thank you, sir. My pleasure. Thank you.
Fine, and thank you.
Thank you, everyone.
रह गया तो